perfect for this talk. I was using Oracle at a small startup, and we had the option of either buying a bunch of, we need to buy a bunch more Oracle instances, and we didn't have the money. So I started shopping around for other databases. At that time, Postgres was on 7.1. And I suggested it to the CTO, and then at my next job, I deployed Postgres. I've been doing Python and Django since 2008. I'm a Django contributor now. And so what's this talk? The idea is to give Python developers just enough Postgres. Now, just enough Postgres is still a fair amount of Postgres, so buckle up. It's going to be kind of a wild ride for the next 3 hours. Because Postgres is a really rich environment. There's a lot of stuff in Postgres. And there's way more than I can dump on you in a single tutorial, and you wouldn't like it if I tried. But we want to get you enough so you can be dangerous with the database. And the reason this is important is before you went and got your Oracle certification, and then the developer went to you and said, we need this schema, it needs to do this and this performance, and you said no. It was a very well understood relationship. But now we have DevOps, and you Google up the term DevOps and you say it's the integration between development and operations. I guess you could guess that from the name. It's cross-functional skill sharing, as if that's something we never did before 2010. And maximum automation development and deployment processes. What it really means is we're too cheap to hire ops staff. And anyway, it's cloud. Cloud solves all problems. So what it really means is you don't have an experienced DBA on staff. You're handed a Postgres, say, oh, by the way, we need to install the database. Could you just go do that and tune it and add some indexes? We need indexes. I was told we need indexes. Anyway, you don't want ops staff. DBAs cost a lot of money. So you're pressed into duty as a database administrator, but that's okay. It's PostgreSQL, because everybody loves PostgreSQL. Just in case you were thinking this was the other PostgreSQL, I'm not sure why you would think this. Postgres is a fully ACID-compliant relational database management system. It has the richest set of features of any modern production DBS. Full stop. Beats Oracle, beats any other database. It has, as a history as a project, it has a very strong focus on quality, security, and spec compliance. If you leave 9.3.1 out. Sorry about that. And it's capable of very high performance. The largest database I personally have ever PSQL'd into on Postgres was over 1 petabyte. So it can handle your database. These people who have 25 megabyte databases and start complaining they need to start sharding, I appreciate the ambition, but you're not quite, don't worry about it. So tens of thousands of transactions per second, in normal databases into the petabyte range, supports everything. So it has become the you can't get fired choice at web startups, which is cool. It runs natively on just about every modern operating system and Windows. It scales from development laptops to giant enterprise clusters, and we're going to talk about how to install it. A lot of information here, so I'm going very fast. So if you have questions or you don't understand something I've said, please do raise your hand. I may have to cue it to a stopping place, but don't sit there and start with the, I was about to say the needle skipping out of the groove, but I guess LPs are cool again, so that's okay. So if you have a package management system, specifically if you're on a Red Hat flavor OS or a Debian flavor OS, use the package manager. Just do it. This will save you endless heartburn. So for one thing, the package maintainer has gone through the trouble of setting it up so that you have the right scripts, it integrates into your environment, the config files are dropped in the right place. So use apt or use yum, depending on which your flavor is. The PostgreSQL project has its own repos for those guys. So you don't have to use the distribution repos. In fact, I would suggest that you don't, because they tend to lag a little bit, especially when there's a new critical release. So if a critical security release has been pushed, those repos will have them right away, whereas the distribution takes just some longer amount of time. No slander on the distribution, the distro repo maintainers, but they've got a lot of other things to maintain. And if you're running on a different OS, there's a variety of packaging systems. You can also build it from source. The good part is this works on any platform that has a compiler. And you get maximum control. There's some things about Postgres that you can only change at compile time. You don't want to change those, but if for some reason you need to, that's the way you do it. And of course, it requires development tools, which not every system comes configured with. And it also, you kind of have to set up your own scripting. So your initd scripts, all that stuff, that's not part of the source tarball for Postgres. So you have to put that together yourself. Maybe that's an advantage if you have specialized requirements. If you go, Windows has a one-click installer available that's maintained by Enterprise DB. That is far and away the preferred way of installing Postgres on Windows. So just a single file you download and run. OS 10 kind of like has gone crazy. Because I do work on Postgres, I build it from source on OS 10. But MacPorts, Brew, Fink, if anyone uses Fink still, and all work. There's also Heroku has a OS 10 style application called Postgres.app that you can download and run, which is really nice because you just fire it up, Postgres starts running, you close the application, Postgres stops running. Very, very nice, so you don't have this, if you don't feel like creating a separate user and having this thing run in the background the whole time. And Postgres.org talks about other things like Solaris and guys like that. So, okay, great. You've installed Postgres by whatever means you have. If you're, I see the usual sea of brightly lit apples out there. If you want to follow along, Postgres.app is probably your best choice. If you otherwise, whatever you like. So, a little bit about Postgres' terminology. This probably deserves a slide that it doesn't have. When you start Postgres, it's a program, like any other program in the world. It has a set of files that it manages and that contain the database. What Postgres traditionally calls that server environment is a cluster. That's not the best term ever in modern world. And in fact, you will hear Postgres people talk about cluster to mean other things, like a set of replication linked servers and things like that. The reason it's called a cluster is what Postgres calls a database, you can have more than one of. So inside of Postgres, once you start it up, you get 3 databases by default called Template 0, Template 1, and Postgres. You don't have to worry about them. They're just there. They give you something to connect to. But you can create more, and you will create more for your own application. So the idea behind the word cluster is, well, you have a cluster of databases. So it's a little bit confusing, but so we're going to use the term server to mean the single Postgres program and all the databases it manages. Once you've installed Postgres, there's a program called initdb, which creates a new database. Postgres has to be up and running, and once Postgres is up and running, you can use initdb to create a new database in it. It connects to the database and issues a create database command. You can actually, all it really is a wrapper around an SQL command. For example, let's just take a look at this. These are a couple of AWS instances I spun up for our amusement here. So I'll go over to this database and go to the Postgres user. And now I'm in the PSQL command line. By default, it connects to the Postgres database. You can tell because it says Postgres there. That's the name of the database. The initdb command is really just a nice little wrapper around typing this. Bang. And you have a new database. And then you can connect to that database. I haven't created any new users, so. Yes. What I can do is make it shorter. Woo. Exciting. Come on. Up you go. No, not select. That's what I get for eating a donut. Okay, there we go. All right. So then I can use PSQL and connect to the new database. And there it is. Really easy. You can also destroy databases with assuming. and it destroys the database and everything in it unrecoverably. So be careful about that. Um, so, and I just made a mistake because initdb does something different than what I was thinking of createdb. And this is a very unfortunate thing, and even though I've been working with Postgres for all these years, I still make this mistake. initdb creates the basic table structure before, and the default databases. We'll talk about createdb in a moment. And it creates the files that will hold the database. It doesn't automatically start the server. Debian style packaging runs this for you. You get a brand new database just by installing Postgres on Debian. And it actually fires it up for you. So by the time the Debian packaging is done, initdb has been run, the database server is running, and it's all set. Red Hat style packaging does not do these steps for you. So you just have to know based on that. So the other nice thing about Debian, if you're on Debian or Ubuntu, is it has a cluster management system. So you can create new database clusters with using command line tools like pgcreate cluster. These are all in the man pages for the package. If you're on Debian, use this stuff. It'll make your life much easier. For one thing, it makes it very easy to run 2 different versions of Postgres at the same time. So it's very helpful. So you're using pgcreate cluster instead of initdb. Always, when you create a new database cluster, a new database, you specify the encoding, the character encoding it's going to use by default. Always use UTF-8. There's exactly one exception, which I'll talk about really briefly later, but just always use UTF-8. Because once you've created it, you can't change it for a database. The other default that you will sometimes see is called SQL ASCII, which is basically raw characters. Don't use that, because if you do and start taking multi-byte characters, you'll be in for a nightmare if you ever want to switch to proper encoding. You can use whatever locale you want. By default, it uses the same one the system is set to. Don't use clocale for the same reason. Clocale basically processes everything as raw bytes, and you don't want that for things like string collation. So by default, in the basic Postgres installation, you get a program called pgctl. It's a built-in command to start and stop Postgres. It's part of the source distribution. Everybody has it. Usually, on your platform, this will be wrapped by platform-specific functionality. For example, let's go back to our friend here at Ubuntu. It's wrapped by service. So you can stop and start the server. So use those if your platform has them. Just once in a while, if service is giving you results that you don't expect, it's kind of nice to be able to drop down to pgctl to start and stop the server. But in general, use whatever the package gives you as for whatever initd or whatever scripts. If you're using pgctl directly, and I'll show you what that looks like. So here we are in the Postgres data directory. Ooh, very scary. You can say, oops, and then you wonder where it is. This is what I always do is like, okay, where did I put the binaries on this one? Oh, there they are. Whee. Okay. So the dash uppercase D is the directory that the database is in, because it uses that to find the process ID and things like that. And ta-da, server is stopped. Now, there are different ways you can stop a server. Let's start it up again. Oh, right. I'm just going to start it this way. And this is a good reason because of the way Debian packaging works. Yeah, it started. It's already stopped. There we go. We'll talk a little bit more about why you want to do this, but there's a -m option on pgctl. Just always say -m fast. trust me on this one. The two other options are, one doesn't work and the other is dangerous. So -mfast is the one you want. Is the right comment. What it does is it will cancel any existing queries, and once those queries are successfully canceled, disconnect everybody, kick everybody out of the server and shut it down. But generally you want to use the package provided scripts. So we already had our brief introduction to PSQL. It's the command line interface to PostgreSQL. It runs queries, you can examine the schema, you can look at Postgres' various internal views, do all sorts of stuff in it. Get a little bit, if you're responsible, if you're the person who gets called when there's a database issue, make sure you know how to get comfortable with this. Log in, play with it, learn the basic commands. Because it's the most direct way of diagnosing database problems. So let's talk a little bit. So when you create a new server in Postgres, what you're really doing is creating a data directory. It's under a top-level directory, which we'll call pgdata as the just. So if you have Postgres installed, go ahead and find it on your system. I'll show you, we can follow along here. Here's what it looks like. This. All the real data, the stuff that you care about, is under this directory base. And there's a bunch of other directories and things. There are no user serviceable parts here, just to be clear. Don't go mucking around inside of this unless you really know what you're doing. Specifically, I'm going to say this because people see this thing called pgxlog. The word log has an unfortunate connotation in computing, which is something a server spits out that isn't all that very important. That is not true of pgxlog. pgxlog and pgclog have a big warning sign on them with a seal on it. Do not go in there. I do get calls sometimes from clients that says, well, this filled up, so we deleted the logs. Which logs? Oh, I have some really bad news for you. Because yes, you can render your database permanently corrupt by deleting stuff in there. So don't do that. Okay. So configuration files. There are really only two that we care about for this purpose. Most installations, the configuration files live in pgdata. Debian, to follow its convention, puts them over here. It puts them in, etc. PostgreSQL, the major version, 9.3, and then a cluster identifier, which is by default main. You can create other clusters also. You can say, main, secondary, or whatever you want to do. So go ahead and find them on your system. The two we're most interested in are PostgreSQL.conf and pghba.conf. Following along here, we go to, etc. PostgreSQL 9.3 main. What did I get wrong? There we go. And so there they are. You notice there's also this PostgreSQL.conf include. I'll explain that in a sec. So all your configuration stuff lives in that. This controls the server configuration. pghba.conf controls who can log in and what they have to do to log in. So authentication to the server. So there are only really two. There are others. If you see other .confs, don't worry about them. So we're going to start with PostgreSQL.conf, because when people say, we want you to configure the server, what they mean is they want to muck around in this file. So find it and open it up, and when you open it up, you'll react like this. There are like 350 control options, and none of them make any sense. It's not that bad, really. It can be like this. I will go through, there are about a dozen things that you need to tweak, and I'll go through what those are. In fact, the reason that you see this include file is what I tend to do is I tend to not edit the PostgreSQL.conf at all, leave it exactly the way it is on stock, and put an include down in the end that includes all the overrides. So I know exactly where the overrides are in one place. You can do this, you can just stick all the overrides at the end textually without having to do a separate file, or you can uncomment them. Pick one of those. Don't do a mixture. It is extremely distressing to see uncommented lines and then play with them and wonder why the heck isn't this changing anything, and realize it's being overridden by something later. So keep all your overrides on one stylistic convention. Because if we look at PostgreSQL.conf include, I mean, it's not empty, but it's much, much smaller than PostgreSQL.conf, and we'll explain exactly what these are all about. Okay. So the important parameters control the following areas. There's logging, which is what it spits out into its text logs while it's operating. Memory configuration, checkpointing, the planner, and that's it. Those are the only 4 areas, and there's only a handful of parameters in each one. Really, you're done. You boot the server and go about your business, and you'll be all fine. So I like to start with logging because to tune some of the other parameters, it's a good idea to have this information. So the first thing I like to do is tweak the logging parameters. The first thing is be generous with logging, especially when you're setting up a new server for a new workload you're not familiar with, a new application. It's generally very low impact, and you really need the data. For finding the top level performance problems, the text logs are the place to start. The first set of parameters control where the files get spat out to. You really have 3 choices here. There's syslog. Use this if you have a syslog infrastructure that you already like for some reason. You know, if you're already using rsyslog and pushing it to a log collector somewhere, no problem. Just go ahead and use syslog. If you have tools that need the old standard format, you may have to use standard format. You probably don't. If you're going, what standard format, what tools, you don't have that problem. So ignore that. Otherwise, log CSV, because it's nice and machine parsable, and it's really easy to use. The next question is, well, okay, now that we've decided what format we're logging in, what should be spat out into the logs? So this is sort of my standard log configuration. Oops, this always happens. You reach the end, back you go. Temp files is the last one. Okay, just a quick rundown. So that says use syslog format. This says put them in the PG log directory inside of PG data. This can be an absolute path also. You can put them wherever you want. By default on Ubuntu, for example, which is not what I'm most familiar with, they go to var log PostgreSQL. The logging collector is a built-in log rotator inside of Postgres. If you're using CSV, you want that on. This is the format of the file name. So this will generate time-stamped files, the date plus the time the log started. This says by default every hour, or every day, excuse me, day. Start a new log file. If the log file hits a gigabyte, which probably means you're logging too much, rotate that to a new one. That's why there's this detailed timestamp there, so they don't collide. This means any statement that takes more than 250 milliseconds to run, put in a log entry that says that happened. That's very handy for finding slow-running queries. You want to log checkpoints, connections, and disconnections, and lock waits. Just trust me on those. We'll talk about why. And saying log temp files 0 means log all temp files that are created, because generally you don't want to see temporary files. And we'll talk about how to tune those. You're done with logging. Logging's fixed. So that was easy. There are really only 3 things you have to tweak in memory: shared buffers, workmem, and maintenance workmem. So shared buffers is really simple. If it's a small system, less than 2 gigabytes, set it to 20% of total system memory. These are assuming this is the only thing running on this box. And I would hope that's true. You generally don't want to run more than one thing on. It always pains me when I see PostgreSQL and a JBoss server and this and that, and then people complain that the PostgreSQL server is running slowly. So set it to 20%. If it's below 32 gigabytes, set it to 25%. If it's above 32 gigabytes, set it to 8 gigabytes. You're done. Don't agonize over this parameter. If people have a, yes? The thing is, people get really like, like, well, should I set it to 7.25 gigabytes or 7.35 gigabytes? And the answer is, we could go to the heat death of the universe and never notice that difference. So the answer is, you can probably, there are some cases where this is not the perfect solution. We'll talk about one of those, the most common of those cases later. But this is fine. The thing to remember is there are really two caches in Postgres. There's shared buffers, which is its level 1 cache, the one that it's really close to. But it also uses the rest of system memory as a file system cache. And you're really moving the line between these two. So the effect is not dramatic to do that. Because I've spent hours tweaking this and trying to get like a big result. You'll notice a factor of 2. You probably won't notice 10%, sort of heuristically. Okay, share buffers, you're done. Workmem. Generally, you want to start this value low, like 32 to 64 megabytes. Then run the system with a realistic workload. And look for log entries that say, I created a temporary file. Because what workmem is the maximum amount of memory Postgres will allocate to things like sort operations and that kind of thing in memory. It's kind of a shame you have to set this, but you do. And set it to 2 to 3 times the largest temp file you see. So if it says I created a 100 megabyte temp file, set it to 300 megabytes. And keep doing that until all your temp files go away. Remembering, and this could be a huge speed up. This can make you seem like a genius. Because the system will be grinding along terribly, you do this, and suddenly all the sorts are running amazingly fast because they're all getting done in memory. One thing to remember, though, is it can burn that amount of memory multiple times per query. So don't go crazy with it. One rule of thumb is if you divide the total amount of system, about half of system free memory, by the number of active connections, that's a good guideline for a maximum. If you would only go as high, let's say a gigabyte or some really large number, if you know there are relatively few connections coming into the machine, or relatively few connections are going to be doing big queries that do huge sorts. Standard sort of web front end kind of workloads tend not to require much in the way of workmem. So maintenance workmem, set it to 10% of system memory up to a gigabyte. Sometimes if vacuum is falling behind, and we'll talk about everybody's favorite topic in PostgreSQL, vacuum, you may have to set it higher. But for now, just start with this. That will probably be fine forever. There is another memory parameter, but this is a little bit different. This is really a planner parameter. It never allocates this much memory. So set this to the amount of file system cache available. You can run like free-m and see how much is being used by buffers. Set it to that. If you don't know, set it to 50% of total system memory. That's a little conservative, but that'll do. This is a hint to the planner of how much will be cached across the whole system, both in shared buffers and in the file system. And that's it. That's all you have to change on memory settings. So checkpointing. Questions on memory settings, by the way. People make this seem like it's an incredibly complicated topic, but it's not. Sir. It's really small. It's like 10 megabytes or something like that. It's almost certainly too small. You can obviously, given the algorithm I just gave, you can set it to whatever you want and run it and see. But I think it's like 10 megabytes. One handy thing is if you look in PostgreSQL.conf, all the commented out values are set to their defaults. So that's a nice way of finding it. Yes? The slides will be up later on the build.com. Yeah. Yeah. Everybody write really quickly. Yes?
Was there any consideration to having a configuration setting where Postgres looks at the amount of system memory and uses those rules of like an automatic setting?
Oh, it comes up on hackers every 18 months without fail, and no one can agree on exactly what the right algorithm is. And there are times that the problem is that in some cases it's workload sensitive, and you can't always guarantee that Postgres is smart about the workload. Shared buffers is an interesting one. By the way, people with Postgres experience from earlier versions, does the old setting schmack schmal thing ring a bell? Anybody? It used to be you had to. There used to be a slide here about tweaking kernel parameters. You don't have to as of 9.3. That problem has gone away in Postgres, where you had to tweak Linux kernel parameters because otherwise it would complain about System 5 shared memory, can't allocate System 5 shared memory. So run 9.3. And there was a question back there, sorry. Oh, absolutely, thank you. Okay, checkpoints. Once in a while, Postgres needs to do a checkpoint, which is basically everything that's in shared buffers gets flushed to disk. Blat. This is potentially a lot of I/O. This is the highest this is generally the most I/O Postgres will ever do. And it does, now the question is, how often does it need to do this? And it does this when one or two thresholds are hit. It's written a particular number of wall segments, and it's fine that your eyes glaze over when I say a particular number of wall segments. We'll talk about what the write-ahead log is and why that's important. Or timeout occurs. Basically, these are just numbers that count up over time. That's all that you have to worry about. So here's what you start with. Just set wall buffers to 16 megabytes. Trust me on this one. There's never a reason for any other value. Set checkpoint completion target at 0.9. You can set checkpoint, this by the way is a syntax error, just to be clear. You pick a number in that range. Don't type literally 10 to 30M. You pick a number there. Higher is better, but higher can require a longer restart time if Postgres crashes. If it's a normal shutdown, it doesn't matter. It'll come right back up. But if it crashes, the higher this value is, the longer it can take. It can take, in theory, as long as that number to come back up. More realistically, it'll take about 20% of that number. So higher is better, but if the answer is, there is no conceivable way I could be down for 30 minutes on a crash, you'll probably want that value to be lower. So, and that's something you just have to look into your heart and decide for yourself. And just start at 32 checkpoint segments of 32. Arbitrary number, don't worry about it, just pick one. Then you run the system and you look in the log for how often it's doing checkpoints. Because you were smart and turned log checkpoints on, it'll tell you every time it does a checkpoint. Are they happening more often than checkpoint timeout? So did you say do a checkpoint every 10 minutes, but they're happening every 7 minutes? Because it's running out of segments, that 32 you saw. Bump up checkpoint segments until it gets to 10 minutes, which is where it'll stop because that's where the timeout is. And when I say bump up, I mean double it. Like 32, 64, 128. Don't tweak this value, just wonk, factor of 2. It'll be fine. And you're done. That's all you have to do. One thing to note is if you're unusually tight on disk space, the write-ahead log can take 3 times 16 megabytes times that checkpoint segment's value on disk at its high watermark. So be aware that bumping up checkpoint segments will burn more disk space. That's not a huge amount of disk space by modern standards, but be aware of it. And from a crash, it can take up to checkpoint timeout. Usually less. Usually about 20% of that value is a good number. Okay, and that's it for checkpoint settings. So planner settings. There are only a few that you have to touch. Effective I/O concurrency. You set this to the number of I/O channels on the main database volume. If you don't know that number, don't set anything. For example, if you're on a RAID 1.0 with 4 disks, you'd probably set it to 4. Basically, the number of I/O operations that can be going on simultaneously. If you're on a 16-channel SSD, you'd set it to 16. But if you look at that and go, I have no idea what this hardware configuration is, or you're on a cloud situation where, just leave it commented out. Random page cost. Here are some guidelines. It's by default, it's 4.0. That is almost certainly too high for any modern system. Like a typical RAID 10 array, 3 is good. If you're on a typical SAN, it's where EBS tends to work best about 1.1. Random page cost, just for historical amusement, is the ratio of how long it takes to fetch a random access page versus a sequential page off of the disk. If you're on an SSD, 1.1 is also a good value. It's not a how fast is this I/O subsystem value, just to be clear. If you're running Postgres off for example, I have a Raspberry Pi with a little flash card. That's the main disk, and random page cost is set to 1.1, not because it's really fast, but because random access and sequential access are pretty much the same speed. on such a device. And you're done with planner settings. There are some things not to mess with. Do not mess with FSync. Leave it commented out. Just don't. Don't. Another one that you probably don't want to touch until you know what it does, but fortunately you're here, so I will explain it to you, is synchronous commit. Because there is some data loss potential, not corruption, but data loss potential on fiddling with synchronous commit. But the one never, ever, ever to touch is FSync. Most settings just require a reload. You don't have to actually restart the server to change them. Things that allocate memory and certain other ones, such as shared buffers, you do actually have to restart the server. One of the nice parts about these is a lot of these you can change on a per session basis. I will give you an example of this because this actually can be quite useful. So you're inside of Postgres and you start a transaction and you say, you know, I was getting I just want to see what random page cost does. So I'm going to say set local, because I can't type. See, can't type. To 2.5. And I'll say show random page cost. Suddenly it's 2.5. And then I say, oh, that was a dumb idea. And now it's back to 1.1. You can also, when you're in PSQL, you can show pretty much any configuration parameter that you set, which is also really nice. If you're going, what's going on? Did I actually change anything? That's very handy. This can be there are times that this can be, you can like send individual queries with different set values. Yes, sir. There's a built-in table that has all these values in them. pgconfig, I always forget the name. So you could just do a select and dump them out that way, or a copy command. And the question was, is there a way of dumping all the overridden values out to a log? One of the columns in that value is, was it overridden? So you can do that. So that's nice. Okay, we're done with PostgreSQL.conf. You now know everything you need to know to tune a Postgres server. That wasn't so bad. Any further questions on PostgreSQL.conf before we talk about PGHBA.conf? Okay. So just a note, Postgres is based around this notion of users and roles. A role roughly corresponds to the notion of a group. They're hierarchical, so a role can be a member of a role, which can be a member of a role, and a role can be a member of multiple roles. So it's a graph, not a tree. It's really complicated, which is a shame because no one uses it. So a role is a database object that can own other objects. It can have tables and it can have privileges. And a user is just a role that can log into the system. Basically, it's a role with the login privilege. Okay. And the security system is all based around users. So the basic user management, here's the basic guidelines. Postgres, when you first initialize Postgres, you get a Postgres user that has the super user privilege, which means all checks are turned off for it. No matter what privileges it has, it can do anything, no matter what. Don't run your application on the Postgres user. Create a new user for the Postgres user. The downside is, since we're all Python people, we're all probably using frameworks with migrations, which need privileges to modify the database, which means you probably have to grant schema modification privileges to your web user, which really kind of sucks. There are ways around it, but this is a very common problem in Django, for example, is that when you apply a schema modification, it logs in as the same user it logs in and everything else as. And it won't work if it doesn't have the privileges. But if there's a way around it, don't do that. One thing to note is, by default, traffic to and from Postgres is not encrypted. It's a boring blog standard TCP/IP connection. So if you're running on any kind of cloud provider and you're not in a VPC, or you don't trust VPC security, which is not a totally irrational thing not to trust, turn on SSL. By the way, everyone's responded to the heartbeat bleed bug? So, before we move on to the wall, I will show you pghba.conf. Yeah, we're in the right place. So, the default one, which unfortunately is overridden here, has a huge comment block on the top telling you what's going on. So that's good. Basically, the way to interpret this is, what type of record is it? You can do authentication based on local, which is to say, just local sockets, or host, which is to say a TCP/IP address. What database this role applies to? All means exactly what it sounds like. It applies to all. What user it applies to? All, but it can be a specific user as well. The address, which in the case of this is blank. And the authentication. Trust means if they have local access to the machine, they must know what they're doing. Let them log in. That's pretty permissive. I would not use that on a production system. There's peer, which means if they're able, for example, you could say local user Postgres method peer, P-E-R. What that means is if the name of the Unix user they're logged in as matches the Postgres user, let them log in. So that means if they are able to log in as the Postgres user on the box, they can connect without a password. That's not actually an irrational thing to do, because if you're the Postgres user, you can get at the data files. So you're not really compromising security on that. For others, this is sort of your standard CIDR type operation. This means the local host. And the method MD5 is MD5 hash password, which is just as secure as it sounds, which is not very. If you're using passwords like MD5 passwords remotely, be sure to turn on SSL. You might also, it is extremely good idea to restrict the addresses very tightly, that only let your web servers connect. Okay. Any questions on pghba.conf? It's pretty straightforward. Now we're going to talk about the write-ahead log. And your first reaction is like, this sounds really detailed and gross, and you're probably right, but the write-ahead log is actually the basis of a lot of the stuff that happens in Postgres. And I think it's important that people understand what it's about, because I mention it a lot. So a lot of what Postgres' technology is built on top of the write-ahead log. Replication is, crash recovery is based on it, all sorts of things. You don't have to worry too much about the internals of what goes on the write-ahead log, just the parts. We'll try to give the high-level view to show you why you need to understand this. So, when you're working on the database, every time you issue a commit statement, all the changes that you made to the database, every modification is flushed out to a file, to a local file. The collection of all those files is called the write-ahead log. It's an important thing to understand that by default, when you say commit, before the prompt comes back, everything has been pushed out safely to disk, which means if you crash, there's a place it can go to get those changes. The way this works is, if there's a crash, Postgres looks for the last checkpoint. Remember those checkpoints where everything was committed onto disk? And replays the write-ahead log, applying the changes that you made again until it comes back up to the present moment. Because at any one moment, the actual on-disk stuff can be completely inconsistent. There can be stuff in memory, there can be stuff that hasn't been written yet, all this stuff. But the write-ahead log will allow it to reach consistency again. So it's a continuous record of the changes since the last checkpoint. When there's a checkpoint, you can think the wall is basically clipped and recycled, because otherwise it would grow forever. You could imagine a database system that never did a checkpoint, and the wall just kept growing forever. That would kind of be impractical, but you could, and restart would take a long time, but conceptually that could work. Now, what this means is, if you have the disk image of the database and every wall record that was created since that disk image was consistent, you can recreate the database at the end of the wall. That's how crash recovery works in Postgres. That's why that pgxlog directory is so important. You need that stuff in the case of a restart. The wall mechanically is stored as 16 megabyte segments in the pgxlog directory. There's a bunch of 16 megabyte files. For example, let's just look at them. There they are. They have these fancy, grotesque names, and they grow in time. And notice they're all exactly 16 megabytes. And it will ultimately, it doesn't aggressively recycle them, but it does recycle them after a while. Don't mess with it. Never delete anything out of it. And Postgres automatically manages the recycling of these. It renames them to the new names. You don't have to deal with all that stuff. That's all taken care of for you. So, okay, we have these wall segments. What could we do with we do with them? Well, we could archive them somewhere. In fact, there's an option called archive command to do that. Archive command is actually a Postgres configuration parameter, and it's a shell command that is run every time a wall segment is complete. It's filled up to that 16 megabytes and started on a new one. It runs this command and says, do something with this, please. It doesn't know what you're doing with it. It doesn't care. It can do whatever you want, set to bin true. But what you want it to do is move that wall segment using rsync or something like that to someplace else that's safe on a different system. Why would you want to do this? Why do you want to keep this huge pile of wall segments around? Because if you have those and the system is completely dead, you can recover using just the wall segments and an image of the database at the previous point. And remember, the longer you have since the checkpoint, the more wall segments it has to process, which is why that checkpoint timeout parameter is important. And we'll talk about wall archiving when we talk about backup and recovery. So now let's talk about that synchronous commit parameter I made scary sounding noises about. By default, which is on, you type commit return, return. Commit doesn't return until the wall flush is done. Everything's on disk. You're safe. You're fine. You're done. But of course, you're waiting for that I/O operation to complete. And that takes time. And that can have throughput consequences. If you turn it off, the commit returns when the wall flush is queued, not when it's done. So you get control back immediately, which is a performance benefit. The problem is you might lose some transactions on a crash because that data hasn't been pushed out to the wall yet. So the application may have seen the commit come back and think everything's fine, I'm done, I'm safe, but then there's a crash and a restart and you're earlier in time than you thought you would be. It's up to you whether or not your application can tolerate that behavior. Some can, some can't. Some are able to reconstruct that data, from another buffer. Some you don't want to deal with that. If you don't want to deal with that, just leave the default as on. Note that there's no danger of data corruption here. The database will always be correct, just earlier in time than it was. Does this make sense to everybody? Okay, nods, great. No danger of database corruption, just to be clear. This is a normal operation. Turning fsync off, big danger of data corruption. Which brings us to backup and recovery. My standard thing is that which exists on only one spindle you do not truly possess. You must back up everything all the time because hardware fails and the cloud providers have made this much worse. There is about a 20% chance when you reboot an Amazon instance, the EBS volumes will not reattach correctly, in my experience, 1 in 5. Sometimes they can't be reattached, period. So what's the answer there? So what are your options on backing up Postgres? Well, the really basic one that we've had forever is the program pgdump. It's a built-in dump and restore tool. It takes a logical snapshot of the database. So at the moment it starts, in effect, the database is frozen as far as it's concerned at that point. Notice that the other users can keep using the database concurrently and modifying it and doing anything they want, except change the schema. But its logical snapshot will be completely consistent. So that's really nice. It doesn't lock the database or prevent writes to disk. Other users are not impacted, except once it has dumped a table, you can't change the schema of it until it completes. That can be a gotcha. It has relatively low load on the database, not 0, but relatively low. Its opposite number is pgrestore. Takes the file that you created from pgdump and recreates the database for you. It's not fast. It can be quite slow. It usually takes between 2 and 3 times the time the PG dump did. It's great for simple backups, but if you're trying to get the system back online really fast from a disaster, especially if it's a big database, that can take a long time. Let's do one and see. So I have this database here. Where's my dump command? I know it's here. There it is. I have a database that's about 1.5 gigabytes. So I just started the dump. So this is, I created this using PGBench. It's a built-in benchmark tool. Chug, 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 chug. So there it's dumping the PGBench accounts. So what it does is at the very start, it starts a transaction in Postgres and does all the dumping inside of a single transaction. So in case people wonder, can you have big transactions in Postgres? Yeah, that's the way pgdump and pgrestore work. Everything operates inside a single transaction. So that wasn't too bad. That was about 1.5 gigabytes being dumped. And let's take a look at the command I used. Notice this -fc option here. That means the custom format. Generally, you want to use the custom format because it lets you do a parallel restore. And we'll talk about why that is. Otherwise, you get what you get out of, if you don't say -fc, you'll get actual SQL commands to restore the data, which is kind of cool. You can go and look at them and edit them if you need to. But generally, you want the custom format. The dump is pretty small. So again, this is the disk size of this database is about 1.5 gigabytes, and this is what? Yeah, that's really tiny. That's about 28-ish megabytes. So nice and compact. It does a little bit of compression also, and we can recreate it here. Where's my restore command? Oh, examples, examples, examples. Let's do a restore here. No, that's where I deleted it. Okay, so here what I'm doing is I'm taking example dump. And I'm saying, create me a new database called example restored with the verbose option there. So, and I have to create example restored first. So I create the new empty database. Bonk. Now this should work, he said confidently. There it goes. So you saw about how long so why does a restore take so much longer? Well, writing generally takes longer than reading, because it has to rebuild data structures. But the big time sink is it doesn't, pgdump does not dump indexes. And pgrestore recreates them. That most of the time is actually index recreation time, not the actual restoring the data. One of the things that you can do, which I'll talk about in a second, is you can do a parallel restore, but you can only do that if you use the custom format, and that can speed things up. So you can see this has taken a little bit longer. And it hasn't actually gotten to the index creation part yet. So let's let that amuse itself in the background, and we'll see. We'll come back to it. Sir?
So I typically just use a TAC app and read a Postgres dump file. Is there a reason I should use restore instead?
Well, you have to use restore if you're using custom format. The question is why can't I just stream the output dump into like PSQL or something like that? And the answer is you can if it's not custom format. If it's custom format, you have to use pgrestore. So, which I talk about here, is you can dump all the global variables like which databases and which users and roles exist using pgdump-globals, and then restore those. And then you dump each database in turn with pgdump. Pgdump can only dump one database at a time. So if you have multiple databases, on the same system, then you need to run pgdump more than once. Yes. Yes, it dumps every database object. So stored procedures, the works. Sorry, are you done yet? No. So it does take a while. To do a parallel restore, use this --jobs option, or -j. That's how many parallel restore jobs it's going to fork off. Generally, I said the number of cores plus 1 is usually about right. The nice part about this is this will parallelize index rebuilding. It also parallelizes the load, but that's the reloading of the data, but that's not as much time. So, and restores are not fast, as we are seeing. Okay. And now you say, well, that's great, but I have a 2 terabyte database, and I'm not planning to do a PG dump on a 2 terabyte database because that would take a week. And I would say, yes, you're absolutely right. So let's do something a little more interesting here, which is PITR, which is short for point in time, backup and recovery. So remember that wall we were talking about? So let's say we took a snapshot of the data directory. And by a snapshot, I mean we just rsync the files across. Nothing special, nothing fancy, no attempt to keep it consistent, just, CP-R if that's what you're into. But if it's consistent, but if we have every wall segment that was created during that period, we can bring it back to consistency. So if we have a disk snapshot and every wall segment that was created during that period, we have a backup of the database. That's pretty cool. So the first thing you need to do to make this work is decide where the wall segments and the backups are going to live. You have to put them somewhere. Don't put them on the same machine. That kind of doesn't make sense for a backup. You configure archive command to stuff the wall segment somewhere. So every time a wall segment's done, it gets copied over. Generally you want to use rsync, not SCP. We'll talk about that when we talk about replication. And then to create the backup, you issue a command to Postgres called start backup. All this does is make sure that there's a wall segment boundary so that you have a specific wall segment you can start from. There's no magic backup mode in Postgres. It doesn't change the operation of the database at all. You copy the disk image. Again, use tar, pipe through SCP, whatever you like, and any wall files that are created during that period. And then select stop backup. And make sure you have all the wall segments. That disk image plus that set of wall segments are your backup. Well, and that's pretty nice. So if this all sounds like real work, I would strongly suggest checking out this Project Wall-E. It's from Heroku. It provides a full set of appropriate scripting. So an archive command, commands to do the backup, and it automatically does the PITR backups into S3, into AWS S3. It also supports Azure Cloud Storage now also and a couple of other things. It's highly recommended. For one thing, it solves, you don't have to write complicated scripts, you don't have to write all this stuff. Very, very handy. And, you have to pay for the S3, but that's not too bad. Okay, now something horrible happened and everything died. So, you copy the disk image back to where you need it. Again, this is your broken, inconsistent disk image that you copied off during the backup. You set up a file called recovery.conf to point to where the wall files are. And I'll show you what a recovery.conf looks like. And you start up Postgres and let it recover. What it'll do is, it'll start up, look and say, oh, inconsistent state, very bad. And use recovery.conf to pull in the wall files one at a time until it reaches the end of the wall stream. And then it will do one of several things depending on how you have it configured, but what you probably in this case want it to do is come back up and be a database server again, and you're done. As it happens, I have a secondary running here, which has a recovery.conf. Oh, look, you finished. That's very nice. So yes, restore does take a while. So here's what a recovery.conf looks like. We'll talk about all this stuff. This looks gross, but it's really all this is saying is it's running Wall-E to grab from this S3 path a segment, because I'm using Wall-E in this example. So, and it'll just repeatedly call this to pull the data in. This also is doing streaming replication, which we'll talk about, but the restore command looks the same, no matter what. So that's pretty nice. So the more wall files you have, the longer it's going to take. The rule of thumb is it generally takes between 10 and 20% of the time it took to create the wall files in the first place. So if it took an hour, it'll take between 6 and 12 minutes to restore. So the more frequently you do these on-disk snapshots, the faster you're going to recover. So why do we keep calling this point-in-time recovery? That's kind of a weird term. You don't have to replay the entire wall. You can stop at a particular timestamp or a particular transaction ID. This is really handy. You get hacked, somebody rolls out a bad application fix that migration that crunches data. The DBA does a drop table and then realizes, oops, that wasn't the staging system, was it? You can recover to a particular point in time right before the bad thing happened. Extremely useful. Okay, sir. Well, there's actually a couple slides on RDS, but there's nothing magic about RDS. It just scripted all this up for you, basically. It's already set up, yes. So, okay, I'd like to take like a 3-minute stretch break. We've been here for an hour, and everybody's, I'm sure, getting attached to their chairs. So, and we'll resume in at 2:24. That's good for you guys. Okay, so the next is, so we went through all that and you went, well, okay, but you still told me this, I'd have to do this long backup and this long copy and remember the 2 terabyte data part. That's going to take forever. I need to be back up to right now, not tomorrow. So what's the answer? And the answer is replication. Hey, what if we didn't like archive this stuff and do all this? What if we just sent the wall directly to another server? Huh, what a brilliant idea. We could keep that server up to date with the primary. It would just get every change the primary made and apply it to itself, and it would stay right up to date. And that's how PostgreSQL replication works. You now understand PostgreSQL replication. All it's doing is sending the wall to another server. There are two different ways it can get the wall to another server, the old way and the new way, but that's all replication does on Postgres. The old way is called wall archiving. You'll occasionally have it called wall shipping or something like that. Every time it completes one of these 16 megabyte segments, it uses that archive command and pushes it to the other server, which absorbs it. Basically, you have an archive command and a recovery command that are kind of pointed at each other, and the recovery command grabs the segment when the archive command sends it over. When the secondary gets the wall segment, it applies it to its copy, just as if it's recovering from a crash. And and make sure archive segment works. Automatically there should be atomically. I clearly was sleepy. One of the things that can break this is if you're using SCP. SCP doesn't do an atomic copy. It creates the file of that name at the moment it starts. That can cause, and then the restore command wakes up, tries to process the wall segment, and gets very unhappy. So use rsync or wally or something that does an atomic copy. Okay, well that's good, but we're still having to move these files around, and that's like gross, and that sounds like my father's technology. So what if we transferred the wall changes directly to the secondary without having to ship the file? Just every time there was a commit, we pushed it over a link. That sounds pretty wild. So it's such a good idea. That's the way Postgres streaming replication works as of 9.0. So when you talk about streaming replication, it's exactly like wall shipping, only it's pushing the wall data down through a TCP/IP connection over the network rather than handing these files over. Generally, you want streaming replication. That's the right way to do to have a server that's going to come up if the primary goes down. The secondary connects to the primary via standard PostgreSQL connection. As the changes happen on the primary, they're sent down to the secondary, and the secondary applies them to its local copy. Just continuously does this. Chug, 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 chug. This is all orchestrated through this recovery.conf file. The recovery.conf always lives in the PG data directory. So even if you're on Ubuntu with the etc. PostgreSQL blah thing, recovery.conf always lives in that data directory. So make sure it's there. And it controls how to connect to the primary, how far to recover, et cetera, et cetera. So let's go back to recovery.conf for a sec. And now we have a little more information about it. So you see that primary con info line. Where's my pointer? This basically says, okay, I'm a secondary, and I'm turned off. Connect to this host IP address on this port using this user, and pick up and have it send changes to me. That's what makes this a streaming replication secondary, is that primary con info line. Don't worry about recovery target timeline. Just set the latest. The trigger file means if this file exists, stop replication and come up as a master. So if the primary crashed and died, you would go in and touch this file, and bang, suddenly this would be a primary. It would exit replication, and now it's a primary. So that's what that line means. You might be thinking, well, okay, but you just said this is dragging these wall segments over. Why do we still need the restore command? It doesn't need to get these files anymore, right? And the answer is yes, unless suppose this network the connection is interrupted for 5 minutes, and then it comes back up and reconnects. The master will go, that's great, but you're way out of date. I don't have that stuff anymore. The restore command can be used to catch it up, and then it will reconnect to the primary that way. So that's very handy. Again, one of the nice parts about S3 is this kind of handles it all for you because you don't have to worry about aging these things out or all that kind of stuff. The archive cleanup command, that is run every time the secondary, this machine, does not need a wall segment anymore. It doesn't matter in the case of S3 because we don't delete those things generally as a matter of policy, or we let S3 do the deletion. But if they were being rsynced over to your machine, obviously they would pile up forever unless we had a way of saying, okay, I processed this, I've ingested it, I'm done, please clean it up. The archive cleanup command is what does that. It's set to bin true here because we throw these away through another process. Okay, questions about that? Great. So disaster recovery. Always have a strategy for disaster recovery if your server contains real data. What if the data center or the AWS region goes down? I talked to a client once, I'm based in San Francisco. San Francisco is remembered for having somewhat unstable seismic situation. They had their servers located in 365 Main, which is built on landfill. They're like ships under it. And I asked them, so, okay, but gonna happen. What happens when the next 7.2 happens here? I said, no problem. Over in Oakland, across the bay, on Phil, we have another data center, which is probably also gonna fall over and burn down in the same earthquake. So, first of all, make sure that you have you're keeping your data in a place that is not where the chance of coincident catastrophes is relatively small. So a remote site, someplace that's not, every place has disasters, but you want them to be unsynchronized disasters. Wall archiving is a great way of handling this because you can push these things over asynchronously as you need to. And presumably, if San Francisco is now in flames, people will forgive you for taking a couple of days to get back online. So you're thinking, well, I need to create all this stuff. I mean, I need to, I talked about how I needed to create, when I'm creating a backup, I need to create a disk image and save the wall files and do all this stuff. That sounds like a lot of scripting. Fortunately, Postgres ships with a tool that does all that for you, called PG Base Backup. It's a utility for doing a snapshot of a running server. It's the easiest way to get a snapshot to start a new secondary. In fact, it uses the replication connection. So one nice part about it is if you can connect with PG Base Backup, you know the replication connection is working. You can also use this to do archival backups. As an example, let's see. If we go over to the secondary here, where's my base backup command? There we go. I saved a couple. So let's say I'm going to be in there. Okay, and it's empty. So I run this command, bang, and the way it goes. What it's doing is connecting, so here's PG Base Backup, it's connected to this host, which is the primary, this user. I'm storing it in a local directory called restore. So that's where the data is going into on my local machine. Xlog method equals stream means that I'm picking up the transaction logs that are being generated while this backup is going on. Checkpoint equals fast, don't worry about that. And the verbose is just generating the stuff you see. So I'm actually doing this whole base backup straight from, the primary right now online. And it's taking a little while. Now it's stalled. AWS, what would we do without you? Chug, 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 chug. There it goes. So yeah. So this is very nice. This is like a one-stop package tool for doing all of those steps that I was talking about that seemed gross and hard to script. I'm waiting for it to stop so I can show you what the result of this interesting looking operation is. You can also have it, right now it's writing to directories, so if you wanted to start up a new server right on top of this directory, you could. It also can write to a tar file if you're doing something that's more like a backup. And away we go. Let's come back to that. So yes, PG Base Backup, very handy. Oh, there's my demo. So. It's much faster when you're setting up the test. Isn't that always the case? Whee! So anyway, yes, what this does is if for example you're setting up a new secondary and you want to do the initial copy, you use PG-based backup for that. Very handy. It is perhaps not always the fastest way of doing it, because it has this custom protocol through the replication connection. It's not as super smart as rsync, but it's foolproof, which counts for a lot in database world. Okay, so the good news about replication, it's very easy to set up. One of the nice parts about the replication is schema changes are automatically propagated down the connection. So on a primary, you modify a table, the secondary will just pick it up. Don't have to do anything special. Changs are automatically picked up. The secondaries can be read from, which is very nice. You can use them to load balance from the primary and the secondary. So you can send read-only queries to the secondary. Read-only queries. Very important note though. There are very few gotchas about string replication. If it connects, it's working. It's very, very hard to break. And if it's broken, it's very conspicuously broken. It's not subtly, weirdly broken, which is very nice. If you're connected and it's staying up to date, you're good, which is very important for something that's important, data recovery, data integrity tool. But of course, nothing's perfect. You have to replicate the entire database cluster or none of it. Every database, every table, every object, everything has to come over. You can't write to the secondary at all in any way. This includes temporary tables, which is really annoying for doing data analysis because temporary tables are really handy for data analysis. But you can't write to the secondary at all, full stop. There are some things that aren't replicated, like temporary tables. You can also set a table to be unlogged. Those are not replicated at all. An unlogged table is sort of a halfway between a regular old table in the database and a temporary table. The fact of its existence is permanent, but the data in it is not. When you restart the database, the data in it is gone, but it still exists as a table. So those aren't set over the replication connection. So my advice for people who are getting started, start with Wall-E. It's really easy to set up. The README will tell you everything you need to know about how to set it up, which is great. There are a lot of really complex replication problems that just get handled for you. Like what if you have multiple secondaries and have to distribute the wall segments out amongst all the secondaries? That's just handled for you by storing everything in S3. And you can set S3 retention policies for how long you want to keep the wall segments. And for backups, you can move them to Glacier and things like that. Very handy. The good part about it is, at some point you'll probably scale out of it because writing to S3 is not super fast, and you probably will want to do something else. But you'll have experience on how all these parts work. So it's a very good, it's a very good sandbox to play in for this stuff. But you're saying no. This will not do at all. I need yes. Before I go on. If you're co-located, would I suggest modifying the wall? You define co-location in this particular case. Wall-E works fine even on your own systems. You don't have to be running on AWS for that. So I would say the biggest limitation at that point is your outbound network connectivity to Amazon. So you may want to try it and see if it keeps up. If it doesn't keep up, then you probably want to do something else and figure out a different place to store the wall segments and things like that. So, but for people who are just getting started, it's not a bad solution. So, the biggest limitation on Wall-E is S3 is not super fast to write to in the best of circumstances, and if your outbound network connectivity to Amazon is slow, that can be a big bottleneck. So that's something you can experiment with. So what if you say, but I really need to only replicate one database or a certain set of tables? Like I have control information that needs to be pushed out. Like I have a users table I want to distribute to everybody, but I don't want to distribute all the other stuff. We have other solutions, which I'm going to lump into the general category of trigger-based replication. This works by installing triggers, which are procedures that run every time a certain event occurs, like you insert a new row or something like that on the master. And then a daemon process picks up these changes and applies them to the secondaries. These are all third-party add-ons to PostgreSQL. 9.4 is building an infrastructure to support all of this stuff, but that's not, 9.4 hasn't been released yet, and the tools don't exist yet. So at the moment, they're all third-party add-ons. Examples of these are Sloaney, which has been around for quite some time, Bucardo, Londiste, those are all trigger-based replication solutions. The good part is they're highly configurable. They have options on their options. If you only want to replicate things that match a certain select pattern, they got you covered. You can push all or part of the tables. You don't have to replicate anything. You have a lot of control. In the case of Bucardo, you can do multi-master setups where two servers are pushing new data to each other, which is kind of handy for load balancing. The bad part is they are really fiddly and complex to set up. They are definitely an advanced course in database administration. And they can, schema changes right now have to be pushed out manually. So if you create a new table on the master, you have to manually tell all the secondaries who created that table, or it will quietly and unpleasantly break. It does impose a lot more overhead on the master than stream replication does, so that's an issue. And one other thing is that I'll mention is that trigger-based replication can break quietly very easily, unlike stream replication, which is pretty noisy anytime it breaks. Okay, and that's replication. Questions, comments, thoughts? Drowning in the fire hose here. Yes?
So like that trigger file that'll tell the secondary to become a master file, how fast does that get picked up? Like say I touch the file.
With sub-second.
Okay.
Yeah. It's by the time you get the prompt back, it'll have probably picked it up and be going at it. Obviously, that's intended to be easy to script also. So, and the question is, how fast does the trigger file get recognized by Postgres? Sir. Correct. Yes. The question is, with the xlog method equals stream option, the backup will be accurate as of the end. The disk image will be, of course, inconsistently recorded throughout the whole thing, but the whole backup will include all the wall files to the end. The reason for the stream, just to give a little bit of a background there, is it picks up each new wall file as it's created, which means that no matter how many are being retained on the master, it'll have them all, which is very handy because the master doesn't retain every single wall file forever. So if the base backup takes 10 minutes, it could easily start recycling them, which means you'd lose some of them in the backup, and that wouldn't be so great. Okay, we're going to talk next about transactions, MVCC, and vacuum, which are, so everybody, like, prop your eyes open. This is a very important part of maintaining Postgres, but it's kind of a fiddly one. You only tend to know about this when something horrible happens, which is awful, but there it is. Everyone knows what a transaction is, right? So it's a unit of which, okay, which must be applied atomically to the database, which is invisible to other database clients until it is committed. So here's the classic example. Everyone uses bank accounts, which is really interesting because no bank in the entire world works this way. You know, they all say, debit this account, credit this account. No bank operates their general ledger this way. Anyway, so, but you insert into transactions a credit and then a debit, or is it a debit then a credit, an add then a subtract, whichever. And and here's the account, and here's the offset account, and you either want them all to run or neither of them to run. Really simple. So here's the things that a transaction has to do to be considered a real live transaction. Once the commit completes, the data has been written into permanent storage, minus that little synchronous commit thing. Pretend that's always on for now. If a database crash occurs, and this is the important one, any transactions will be either committed or not. There are no half-done transactions. You don't get halfway through. And no transaction can directly see another transaction in progress. So if I say commit, if I say begin and do the first one, no query in the world will pick up that first one until the commit happens, except for my queries, of course. My local session sees my own work. In PostgreSQL, everything runs inside a transaction. There's no way to not have a transaction in Postgres. If you don't have an explicit transaction, you just type a single line, there's an implicit begin and commit wrapping that single statement. Okay, that sounds fine. This has certain consequences if you're writing stored procedures, because it means that stored procedure runs entirely inside a single transaction. There's no transaction control possible inside of that, which can be kind of annoying sometimes, but there it is. One of the things about Postgres is that everything that modifies the database is transactional, even schema changes. This is really, this is a huge feature of Postgres that people do not fully appreciate. For example, here I am on the primary, and I'm an example. And I type \d, which shows me all my tables. And I type begin, and I say do. I have no idea what I'm doing here. I'm just going to type some random stuff. Oh, darn. I did not want to do that. Okay. I didn't. You can roll back schema modifications in Postgres. Anyone have Oracle experience? How much would you like this? Yeah. I'm sorry? Yes. South runs everything inside a single transaction, which is why Andrew Godwin, the South author, says use Postgres, use Postgres, use Postgres. So this is really nice. I now have the habit of just typing begin before I start mucking with the database, just in case. Sir? You can only roll back the current open transaction. Once a transaction has been committed, you're stuck with it, sadly. There are such things as save points, which kind of are like nested transactions, but the outermost transaction, once you commit, hope that's what you meant. So that's why point-in-time recovery is very handy. So one thing about transactions to note is many resources are held till the end of transactions. Temporary tables, working memory, locks, all sorts of stuff is only released when a transaction commits or rolls back. This is a good reason to keep your transactions brief and to the point, because if you leave a transaction dangling open and it has a lot of resources blocked up, other things can start tripping over them. And especially beware of sessions that are listed as idle in transaction. We'll talk a little bit about that. This is particularly a big problem for Django applications. Transaction management would be easy if databases were single user, but they're not. Thank goodness, because that would be kind of a pain. So how do we handle concurrency control when two sessions are trying to use the same data at the same time? So here's an example. Process 1 begins a transaction. Process 2 updates a tuple. A tuple and a row are the same thing. Postgres for historical reasons likes to call them tuples, but they're the same thing. And process 2 reads that same tuple. What happens in this scenario? Well, bad things. Process 2 can't get the new version of the tuple by database rules, because that would be a dirty read, and we don't want dirty reads. But where does it get that old version from? The first process has changed that data. So where is that old data living? Does it keep it in memory? Does it keep it in disk? Does it keep it in a special rollback area? And what if we touch 250 million rows? Where are all those old versions going to go? So some approaches, we lock the whole database. That's not going to fly very well. This was the MongoDB, used to be the MongoDB answer. Then they decided that didn't work, so they decided to lock the whole table. Or we could lock that particular tuple. We just block and wait for the transaction to commit, and then we pick up the new version. But you can imagine that's kind of like not going to fly on concurrency. Or we keep the old versions around in some special area and reconstruct that old state on the fly. And all of these have pretty obvious, straightforward problems. Postgres doesn't use any of those. Postgres does a thing called multi-version concurrency control. The old version and the new version are still around in the database at the same time. Each transaction only sees its version of the tuple. So in effect, the database has split into two separate versions. What Postgres calls these snapshots internally. And snapshots are first-class members of the database. There's no privileged real snapshot in Postgres. Each transaction sees its own version of the data. The nice part about this is readers don't block readers. That would be pretty horrible if they did. Readers don't block writers, and writers don't block readers to the same data. The only thing that blocks are writers block writers if they are updating the same tuple. So if two different processes try and modify the same row, they'll block. Each transaction has its own snapshot. The transactions create when a snapshot or a transaction starts, depending on what's called the transaction isolation mode. We'll talk a little bit about that. And the client only sees the changes in its own snapshot. So once you say begin, you're kind of in your own world as far as the database is concerned. You generally will see other transactions that have been committed by other sessions. Once they commit, that data will appear in your snapshot. But otherwise, the things you do, they live in their own world. They don't affect anyone else. This isn't perfect, though, because you can't fork the database and then recombine it in some merge operation. And so Postgres uses locking to prevent that from ever happening. So if like two sessions try to modify the same tuple, one will block, waiting for the other to commit or roll back. And then it'll proceed with whatever it was trying to do. Generally, the most common case of this kind of conflict is two separate clients, two separate sessions are trying to update the same tuple. There are 3 isolation modes that Postgres supports, which is read committed, repeatable read, and serializable. It doesn't support read uncommitted, which is in the standard as a way of enabling dirty read. Postgres architecturally can't support that, so it doesn't. So a snapshot is logically all the transactions that have been committed to a particular point in time. You can even manipulate them. You can save and load snapshots. That's pretty wild, but they're integral to how Postgres works. So a snapshot begins when, in read committed mode, each statement starts its own snapshot. So it samples the committed state of the database across the whole database at that point, and it sees every committed transaction. So it will see other people's transactions being committed. So it sees anything that's been committed since the last statement. If you attempt to update a tuple that another tuple is updated, you'll block, waiting for that other transaction to commit. That's not the only behavior possible, though. Repeatable read and serializable take the snapshot when the transaction begins. Once you say begin, no one else's work affects you. Your database, as far as you're concerned, you're the only client in that database. Other clients can mess with the database all they want. You won't see any of those changes. That's what PG dump does. Is it starts a transaction in repeatable read mode and gets a perfectly consistent dump of the entire database. And it lasts until the end when you commit. The problem is, if you attempt to modify a tuple, another transaction is tuple, it blocks and it returns an error if that transaction commits, because it can't maintain the illusion that you're the only client of the database anymore. So you're running along, somebody else modifies a tuple, you modify the same one, you stop. If it rolls back, that's fine, because it's the old value, and that was the old value you saw. The problem is, if it commits, you can't modify that. You can't modify because that would require some kind of weird merge operation at the end. Which one would win in this case? So what happens is you get an error that's called a serializability error, and it says, sorry, couldn't maintain the illusion anymore. Try again. And what the program generally does in that case is it loops back to the top and tries the transaction again. Again, it maintains the illusion of a perfect snapshot, but if it can't, it throws an error. So you can retry it. Serializable is kind of is a super repeatable read, because not every conflict that's possible can be detected at the single tuple level. For example, if you're inserting calculated values, there are situations in which the behavior will change depending on other people's work, but just row-level locking won't detect that. Serializable has this fancy predicate locking mechanism. It requires a little bit of overhead. The reason I mentioned it is I actually recommend that new database applications run in serializable mode, because you will discover a lot of interesting assumptions that you made about concurrency that you might not have realized by these errors. And you can look at what your code is doing. So set it by default in the database to serializable. Okay. One of the consequences of MVCC, though, and the reason that this is important from a database management perspective, is when you delete a tuple, it's not immediately released back as free space, because somebody else might be able to see it. You can imagine that if you delete a tuple, but somebody else has a transaction running over here, they can still see that tuple. It's still a perfectly good tuple in the database. So a delete operation by itself can't immediately drop it back into the free space. And doing this check on every delete would be prohibitively expensive because you'd have to look at every snapshot and every open transaction, and that would be horrible. The result is you end up with dead tuples in the database that are not visible to any transaction. Nobody can ever see them, but we haven't reclaimed them yet. And what reclaims them is vacuum. That's what vacuum does. That's why it's important to vacuum a Postgres database. This is the primary job. It scavenges all the dead tuples and reclaims them. And if it sees one that can't be seen by any transaction, it marks it as reclaimed and puts it back for reuse. The good part is, since version 8, actually, of Postgres, there's a daemon that runs in the background inside Postgres called AutoVacuum. And it does this automatically for you without you having to do a thing. You don't have to manually vacuum the database. You generally don't have to worry about it. So that's great. Vacuum also has another component called analyze, which is the planner requires statistics on the distribution of values in the tables to get good guesses, and analyze collects those. And this is done as a part of vacuum. So that's the only time you have to worry about analyze is if you do a major database change, like you restore it from a backup, or you've done a massive bulk insert or something like that. Doing a manual analyze across the whole database is a really good idea to rebuild the planner statistics, because AutoVacuum may not catch up right away. And one thing, okay, you'll get the call and say, vacuum's not working. And you'll say, what do you mean vacuum's not working? Please define your terms. The answer is, yeah, vacuum's probably working. The first thing that people look at is the database seems big for the amount of data. Because of this dead tuple and MVCC situation, generally the database will stabilize about 20 to 50% bloat. That's acceptable in Postgres. So having between 20 and 50% of the database being dead space, that's acceptable. So don't panic if the database is, what'll happen is it'll increase, and then as the database is modified and updated, it'll slowly slow down. If it's growing without limit, that's a problem, but that's generally acceptable. The other thing people mean when they say vacuum's not working is every time you look, the AutoVacuum workers are going. By itself, that's not a problem. They're supposed to be going. That's what they do. So don't panic if you see AutoVacuum workers in the background running all the time. But you say, no, really, vacuum's not working. For example, you can look at pgstat user tables, and it'll tell you the last time a table was vacuumed or analyzed. And there's a table that's very busy, that's being updated all the time, but the vacuum time was way in the past. That could be a problem. So the first thing to look at is, do you have really long-running transactions, or even worse, idle in transaction sessions? A session which started a transaction and then somebody walked away, somebody being either a human or the computer, and left it open, because those will block vacuuming, because as far as the Postgres is concerned, those tuples are still visible to that transaction. Are you doing manual table locking as part of your application? Because if you manually lock a table, the program actually issues a lock table command. AutoVacuum can't touch that table to do the vacuuming. And if that's something that happens all the time, vacuum keeps bouncing off that table and is unable to run on it. Very high write rate tables, sometimes the AutoVacuum daemon can't keep up, especially if they're very high update rate tables. You have lots and lots of tables, like 10,000 or more. That seems ridiculous, but for example, if you have some kinds of sharding architectures, we'll end up with 10,000 to 100,000 tables. So that is not as ridiculous as it sounds. So what do you do? There's a sleep time value in AutoVacuum you can reduce. That's the first thing you usually try. Especially if you have lots and lots of tables, increasing the number of AutoVacuum workers. By default, it's 3, but you can bump it up to 5 or 7. That's a good place to start. Or do low period manual vacuums. This is especially helpful if AutoVacuum is waking up at bad times and causing a lot of I/O. And of course, fix the bugs. Fix idle on transaction sessions, long transactions, manual locking. Okay. And that really is everything you need to know to administer a Postgres database. That was easy. See, talked myself out of a job. Questions about that before we launch onto the more application-y kind of stuff? I believe the next break is at 3:30, yes? Does that sound correct to everybody? Nodding, yeah, okay. Great, so we're going to talk a little bit now about schema design. Pop up a level. So schema design is obviously a huge topic, and everybody uses different ORMs, and there's all sorts of things to talk about. But so this will be a little bit of a once over lightly, but I think it'll help. So one of the things you'll always hear about is normal form. Database people are always banging on about normal form. Everything that's this normal form. I don't, what's their normal form? I don't remember. Who cares? But normalization is important, but don't obsess about it. Don't, if somebody comes to you and looks at it and says, is this in third normal form, just give them a look. Normalization actually generally flows naturally from proper separation of data. When you're designing a schema, generally you pick entities, like the top level logical objects in your data model, customers, orders, models, and just flow down from that to subsidiary items. The schema kind of designs itself from there. The important thing is first make sure that no entity level information gets pushed into the subsidiary items. If you have an order item, it shouldn't have the customer's name in it. Basic stuff like that. Keep the data, if something's an attribute of one of these things, keep it in that thing. Don't push it down into that stuff. One thing about schema design that really drives me nuts is, are tables plural or singular? Just pick one and stick with it. Doesn't matter to me. Database people tend to like plurals because they're collection, because we think of a table as a collection of things. It's orders because all the orders are in the orders table. ORMs tend to like singular because they're thinking of it as an order object, and so they're thinking in the singular class sense. Doesn't matter. No one cares. Just pick one. Camel case or lowercase or what? Just pick one. You'd probably want lowercase because you'll save yourself having to type a lot of stupid double quotes in SQL. Really, normalization is just another form of don't repeat yourself. What denormalization generally means is including data in a table that you could have gotten from another table, that you didn't have to get out, that it didn't have to be there. You could have calculated it on the fly. You can either because you copied the data or you calculated it. A good general rule of thumb is that calculated denormalization can sometimes be useful. For example, if you have an order object and you need the total of that order, technically it is a denormalization to put the total in that because you could have calculated it from all the line items. Anytime, just on the fly. It's a query, it's a join. Databases are good at that. Is that necessarily the right thing to do, or does having the total in the order make sense because because that way it's right there and you don't have to do this big join every time you do? Yeah, I could be sold on that. I'd want to see, I'd only do it if on the basis of real life performance numbers, of course. Don't just denormalize things because you think maybe. But if the data, but that's reasonable. Copying data is usually never a great idea. Pushing the order, it's like, I'll see sometimes, how many people use Django before I, woo, dude. I'll see things like customer names pushed into the order because that way they only have to put the order in the view context, in the template context. And it's like, painful. Because what if they get out of sync? How are you planning to keep these in sync? All this stuff. So if it's just a matter of copying data from one thing to another, don't do that. One thing, yes?
I have to admit, I tend to do that all the time with, customers. We have our database isn't completely clean, so we've got duplicate records of products and customers, and the products can have their descriptions changed. I want a snapshot of that order. I want the description name on the customer.
Right, and I would. The question is, there's sometimes that what kind of looks like a denormalization, like for example, pricing is a great example. In a line item, it has the price of the item as it was at the time that line item was created, and then you bump the price up or down later. That I wouldn't call a denormalization because those are two different facts. When you're thinking about it, one's the price at order, one's the price of the item associated with that order. The other one's like a standard list price and things like that. That does happen. The thing is, but what you don't want to do is like a customer name. If the customer changes their name for some reason, they get married or whatever, and then you'd have to push that into all the objects. You've made a mistake then. At the point that you're like pushing this data out again manually into all the other objects. So, because joins are fast. You generally want to, if it's just being used to annotate objects like that, just keep it where it's supposed to be. one of the things that shows, though, is there's no like absolute certain rule that will apply in every single case. You know, I can be persuaded for along a large number of denormalizations. But generally, joins are good. Postgres executes joins very efficiently. Don't be afraid of them. Use the join thing. I will say, as a Django person, the ORM query syntax does not make one super comfortable with joins because they get out of control really fast. But still, do joins. Especially large tables joining small tables. Or large sets joining smaller sets. This executes really efficiently in Postgres. Another thing is use the typing system. Postgres has an amazingly rich set of types. Use them. If something's a numeric, don't store it as a string, for crying out loud. Don't use string to be a generic blob holder as a way of defeating the typing system. Postgres has a functionality called domains. If you're not stuck with an ORM that doesn't support them, you can use a domain is basically a type, is a core type plus a constraint. So you can say things like, okay, I want to create a price item that is a numeric of this size that has to be positive. And that's a very handy feature. Don't create polymorphic fields. Avoid fields whose interpretation is dependent on another field, like the attribute, this is color or weight or height or width or this, and this is the value for it. Don't do fields like that. You'll go crazy trying to do reporting. Don't use fields, strings, to defeat the typing system. Keep each field well defined. Have it be a thing, an object, a particular thing. Use constraints. Try and avoid, to the extent possible, bad data ever getting into the database. If a price can't be negative, make sure there's a constraint on that line, on that field that says the price can't be negative. You can have constraints on single columns. You can also have constraints on multiple columns. So if there's a particular set of values that have to be true as a set, you can do that in Postgres. You can even do a thing called an exclusion constraint, which allows you to, which is sort of like the reverse of a unique. And you can do constraints that are that enforce consistency across multiple rows. Oops, duplicate slide. And whatever you do, avoid EAV schemas. An EAV schema is something where there are three columns. There's the thing, the attribute, and the value of that attribute. And rather than have separate columns, you just have more rows that represent more attributes. You will kill yourself eventually doing this. Somebody will come in and ask for a report, and you will be there until 3 in the morning trying to make it work. They're nightmares to join and report on. They're very inefficient. And big database bloat. So picking primary keys. If you use Django, you're probably, you're used to using auto, and that's fine. That maps to serial inside of Postgres, a counter, which is convenient and straightforward. But what happens if you have to merge two tables or two databases? Generally, try and use natural keys whenever possible, keys that evolve out of the nature of the data. One of the problems, of course, is that people don't have natural keys. You could look through history and see all the attempts people have made to give people natural keys. There were social security numbers, in the U.S., and now we can't use those anymore, and blah, blah, blah. So sometimes you have to use synthetic keys. One thing to think about is use UUIDs as the primary key. Basically, they're big random numbers. But the nice part about it is merging two tables is probably not going to be an issue. Don't have thing tables, Sometimes OO programmers like to have table hierarchies, and unfortunately Django encourages this with its model inheritance stuff. The problem is they tend to have these big base tables with common attributes factored out, and it looks normalized, but it's really a pain in the neck. So don't have like an object table that then have orders and customers descending from object. Not a good idea. Another bit about schema design that I like to encourage is what I call the fast-slow rule. Very frequently you'll have a table which has stuff that changes really fast and stuff that rarely changes. For example, a user. User in Django is the most common, is a great example of this. You have the primary key, that never changes. You have the email address, that changes, but not all that often. And then you have all these other stuff, and then you have like last clicked, which changes all the time. You'll get into all sorts of trouble if you lump all these into the same table because of locking problems. If every time somebody clicks, you have to update the user table, that can create huge locking problems because everything refers to the user table. So take all the really fast, the fast moving stuff and make it its own table that has a one-to-one relationship with the base table. Because foreign key locking in Postgres can be an issue when you when you have two tables, an A and a B, and the B points to A, and you update a row in B, the row in A that's pointed to also has a lock taken on it. And if that is the user object, which everything has to read, that can be a problem. Arrays in Postgres. Arrays are a first-class type in Postgres. You can have a field that is an array. You can search them, you can index them, you can do all sorts of stuff with them. Often, this is a good substitute for a subsidiary table. For example, a list of tags can often be better represented as an array than as a subsidiary table. Yes? Depends on how much time series data we're talking about. At that, I would say assuming you don't need to do the kind of searching and joining operations, you're always processing it as a unit. I would say that's not a bad choice. Like lists of tags are a great example of things that are often better implemented as an array. Like you're tagging, where the tags are just integers that point into another table or something like that. That's often a better solution than a many-to-many table. HStore. HStore is a hash. It's like a Python dict structure built into Postgres. This is great for optional variable attributes. For example, you have clothing or something like that, and you have all the standard stuff, but then you have other things that may or may not be present. Like you may have a multiple value fabric column or something like that. That not most rows don't have, but some do. So it's basically a hash type. It's or a dictionary type. Very handy. This is also handy if you're using a packaged application that you're shipping to customers, but that you want them to be able to add rows, to add attributes to a field, but you don't want them to an item like you're selling on an e-commerce system, and you want them to be able to create their own private attributes on items, but you don't want to modify the schema. This is a great place to store things like that. And now we have JSON as a first-class type. It doesn't have quite as many indexing or searching things as HStore, but it's getting there. 9.4 will have a lot more. So if you're doing brand new work, I would suggest using JSON instead of HStore, or specifically use JSONB, which is a binary representation of JSON that's much faster in 9.4. You can also use this to, if you have JSON data that you're storing, like caching or things like that, you can store it in these. It's very nice. If you're indexing a big type, where let's say big is like a 2K character string or something like that, Postgres will do this, but it can be kind of inefficient. One thing you might consider is like indexing on the first 32 and last 16 characters of the string, and then searching on that basis and then filtering out the rest of them. Searching on just indexing the high entropy parts, because indexes on very large types in Postgres are not super efficient, like 10K character strings or things like that. So that's a little trick. Null. If you think you understand what null means, you don't, because null is a total pain in the neck. You have to deal with it. You can't get away from it in databases, but the only thing you should use null for is to mean missing value. Don't use it as a semantically interesting value in your schema. And never, ever, ever have it be a meaningful value in a key field, because it will not work the way you expect, because null does not equal null. And thus searching on null can be very, very confusing and get you results. So you can't get away from null, but only use it to mean a hole in the data. That means I have no idea what this value is. One thing that is unfortunate that people kind of get into, and Postgres heroically tries to support this, is very large objects like images, or heaven help us all, video streams. Let's call a large object a megabyte or more. Let's just make up a number. If you do this, store them in a file. Every modern operating system comes with a database which is optimized for storing large byte streams. It's called a file system. Use it. Just store the metadata, file pointers, or something like that in the database. Don't store them directly in the database. It's just not a good API for throwing this stuff around. Generally, you have to return them as a unit rather than streaming, which is not great for a 1 gigabyte object. And Postgres will do it. You can store, the largest individual thing that you can store in Postgres is 1 gigabyte, and you can have an entire row of 1 gigabyte fields. And Postgres will make it work, but you probably won't like it. Into every life, a little many too many tables must fall. The problem is this is where you have two things that are related to each other that mean exactly what they say. For example, people and the posts they like is the classic example of a many to many table. This is a good thing that you can replace with array fields. The problem is that many to many fields are an O(n) squared growth pattern, and they can be really slow to join over when they get to be huge. You can either do one way or both directions. The thing to think about is, so what question are you usually asking? Am I usually asking which people like this post? In which case, probably an array field on the post makes sense. Am I usually asking which people, what post does this person like? In which case, an array field on the person might make sense. You can use a trigger to maintain the integrity on array fields. And they generally are smaller and more efficient. Of course, at the point that somebody could like 1 million posts, or some individual could like 5 million posts, or one post could be liked by 5 million people, probably sticking them in an array is not a good idea. But that's a fairly complicated schema design question. Sir?
What's the pragmatic limit to when arrays are effective as far as size?
About a megabyte. So, that's about what, 250,000 entries would be my guess. That's totally a rule of thumb because it depends on your usage pattern. The question is, how big can an array be before it starts becoming impractical as a unit? Yeah, so of course that depends on your usage model. I'm going to bang on once more about character encoding. Use UTF-8. Just use UTF-8. There's no compelling. UTF-8 is probably the best solution we are ever going to get in any of our lifetimes to the character encoding problem. That's not to say it's the best solution, but it's what we got, and it's what we're always going to have. There's one, I promised you there was one edge case, and there is. If your bottleneck is sorting strings in the database, SQL ASCII is faster, is quite a bit faster. It's probably not your bottleneck. It is very rarely your bottleneck. And let me know if this is it, because it does happen. But generally, just use UTF-8. Always initialize your database as that. Converting from any other encoding, or worse yet, random arbitrary encodings, because the situation you don't want to find yourself in is everybody on had whatever encoding their browser happened to be set to, was dumping data into your database, and you have 23 different encodings inside your database, and you have to sort that out. Nightmare. Very bad. This is my personal pet peeve. Always use timestamp TZ. It's what you get by default for a date time in Django, for example. Postgres has timestamp. Don't use it. If you think you've come up with a use case for timestamp, you are wrong. Think again. Timestamp TZ, they are exactly the same size. Timestamp TZ is short for timestamp with time zone, which is a very misleading name. It doesn't actually store the time zone in the timestamp. What it means is this timestamp is guaranteed to be in UTC. So timestamp is timestamp at some time zone, which we hope you know which time zone it was. So whenever you convert out a timestamp TZ, it will convert it using the time zone of the server and the client as appropriate. So you'll get it back in a reasonable time zone. Timestamp will just be handed back raw and hope you know what you're talking about. So always use timestamp TZ. Because the first time you run into multi-time zone data, you'll be very glad you did. Sir? Okay. Okay. And now, let's see. Yes, we'll blaze through to indexing and then have the break. So, test your database knowledge. What does the SQL standard require for indexes? No fair anyone who's ever taken a class from me before, because I always ask this question. Anyone know the answer? Yes. Trick question. It doesn't require anything. They aren't mentioned in the SQL standard. Because the database should work identically whether or not you have indexes. Of course, identically doesn't mean just as fast. It just means the same result. But the problem is no real-life database can properly work without indexes. You die. So Postgres has a bunch of index types, of which we will talk about 3. We're not going to talk about hash because you shouldn't use it. And we're not going to talk about SPGIST because it's very, very niche case use. But we'll talk about btree, gist, and gin. Your basic log standard, you type create index, you've got an index is a btree. It provides O-log-N access to leaf nodes. It provides total ordering, so you can walk the data in both directions, very nice. And it operates on any scalar value that implements the standard comparison operators. So anything that you can compare greater than or less than to and has sensible greater than or less than behavior, you can index on. You can do a single column index, you can do a multi-column index, which is an underused feature, and you can do expression or functional indexes. When you just say create index on this column, what you get is a single column btree. It can optimize searches on any of these operations, on the standard comparison. You can also use it to retrieve rows in sorted order on that column, which is very nice if you're doing it, because Postgres is usually smart enough to be able to, when you're doing, you retrieve things in a sorted order, like with a sort operation, it can walk the index if the result set is small enough. So when do you want to create a btree index on a column? If a query uses that column and uses one of the comparison operators, and this is very important, this is the one people tend to get wrong, if that query is going to select between 10 and 15% of the rows and no more, and it's frequently run, the index will be helpful. This is based on what's called the selectivity of the query. If it's a very high selectivity, like say you're going to get, let's say you have a database that's a large number of people, and you have a Boolean, you have a Boolean value in there that's roughly 50% distributed. An index will not help you on that, because walking an index is much more expensive than reading things in sequential order on a row-by-row basis. So the only reason it will be helpful is if you're retrieving a small number of the rows. However, if you're retrieving by last name, it probably will be helpful unless the last name is Smith or something. You know, has a very high hit rate. But even then, probably, I don't know what the cardinality of Smith is in the US or in North America. But that's the important thing to remember. A lot of the why isn't it using my index questions are because Postgres doesn't think it meets this criteria, and it does a sequential scan instead. So indexes can accelerate joins with the usual rules about selectivity. Generally, they help the most when you're joining a large table to a small table, and you're querying the join is on the index is on the key on the larger table, and that results in a high selectivity on the smaller table. That particular situation is very heavily accelerated by an index. Some group bys and related things can benefit from an index. Usually you need a having clause, which most ORMs never generate, so you don't have to worry too much about that. And remember, if it has to scan the entire index, it might as well scan the whole table. It's much faster to do a sequential scan of the whole table than to walk an index scanning the whole table by orders of magnitude. And some indexes you just can't get away from. Primary keys have to have indexes to enforce uniqueness, and just accept those. You have the option of building an index either ascending or descending. By default, they're in ascending order. If the main thing you're trying to do is like get the last 5 things out of a table, that's your like core operation, that's the most important thing is just get me the last 5 things out of this table, then a descending index will help you a lot. Otherwise, just use ascending. Composite indexes can be very helpful. You can have a single index that has multiple columns. You have to use them left to right. So if you create your index on ABC and you just query on C, that's not going to help you at all. Index is useless. But it does help you on A and B, and it also helps you on just A. So if you're doing queries of the form where last name equals this and first name equals that, an index on both last name comma first name might be the right thing to do. Expression indexes, which are indexes on expression, you probably could have guessed that. For example, you could index on lowercase of name. And then if your query is where lowercase on name equals string, Postgres is smart enough to recognize that it's the same expression in both places and use the index. They can be a little expensive to create depending on how complicated it is, but they can be very fast to execute. Make sure Postgres is actually using it, because you don't want to build this giant expensive index and then discover Postgres isn't using it for anything. We'll talk about how to do that in a moment. An underutilized feature of Postgres is called a partial index. An index doesn't have to index every row in the table. You can add a when clause. So for example, this is really handy for highly selective Boolean queries. For example, suppose you have an orders table, and one of the fields is active, and only 2% of your orders are active at any one time. You could create an index when active, and then if you are doing a query either on active directly or on something else and active, it will use that index. And that can be a huge time accelerator because it's a very small index to walk. Sir?
Do you have multiple partial indexes on one table?
Yes, as many as you want. Remember though, every index you create is an index that has to update on every insert. So be aware of that.
So it's better for read heavy than write.
Yeah, exactly. Sir?
What happens if conditions overlap?
No big deal. I mean, Postgres it's somewhat non-deterministic. The question is if you have the when predicates overlap on two different indexes. And it's somewhat non-deterministic which one Postgres will use. I'm not sure how smart the query planner is in that precise area. Be interested to know. It'll unlikely hurt you though. So that's there, and it's not an error, definitely. One thing to note is about multi-version concurrency control is that the full key value is copied into the index. And every version of the tuple on the disk appears in the index because every different tuple is a potentially live candidate for an index search. So Postgres actually has to check on an index retrieval whether a retrieved tuple is live. This means indexes can bloat because of dead tuples. The answer to this is make sure your vacuuming stays up to date because vacuuming helps this. And that's B-tree indexes. Postgres also has a thing called a gist index. It's not really an index type, it's a framework for different indexes. You can use it to create B-tree style indexes, but you can also use it to create, and where it's most interesting, is you can use it to create other index types like bounding box and geometric queries. Like, is this point inside this rectangle? And notice that point and rectangle are built-in types in Postgres. You don't even have to have PostGIS for it. So generally types that you want to index but aren't totally ordered, where you can't, is this point greater than this point is not a meaningful operation. But are both these points on this line is a meaningful operation. Each type has its own index implementation and decides what to support, which could be inclusion or membership or intersection or all the various things, both geometric and set operations and things like that. Some gist indexes do provide ordering. One relatively new feature, like 3 or 4 years, is KNN for K nearest neighbor index. This actually solves what I call the Starbucks problem, which is I want the 5 Starbucks closest to me. You would think that any geometric database geometric type, that would be like a built-in operation. It's actually a really hard operation without a KNN index because what you have is a bounding box and the ability to sort. Well, but if I'm trying to find all the nearest coffee places to where I am now, here in Montreal, that's one thing. If I'm out in the wild somewhere, the bounding box has to be much larger, and picking that bounding box is complicated. KNN actually solves that problem and hands you the top 5 nearest Starbucks. So finally, we have a solution to that. There's also GIN indexes, which is short for a generalized inverted index. I'm not sure which I goes where. What a GIN index does is it maps index types like words or dictionary keys into rows whose fields contain them. So The basic thing this is used for in core Postgres is the full-text search functionality of Postgres. Postgres does have built-in full-text search, and KNN indexes are the base index type. It maps the tokenized words to the rows containing these words. And if you're interested, it's a B tree of B trees. The tokens are organized into B trees, and the row borders are also organized into B trees. The reason this is important is these suckers can be big. They're very large, but they're very fast for their specific use case. Okay, and we're going to take a break now. Let's come back at about 5, and we'll talk about why isn't it using my indexes. Okay, 1, 2, 3, and there we are. Okay, so you've created all these fancy super indexes, and then you run a query and it doesn't use them. Why is that? What have I done to deserve this fate? So first, get the explain, analyze output of the query. We'll talk a little bit about how to do that. And sometimes it's using the index that's just slow anyway. There it is, there's the index, and it's just a slow query that's processing a lot of data. The most common reason, though, that if it's not using the index is bad selectivity. If it thinks that the index scan is going to return a large number of rows, it'll do a sequential scan instead, because that's much faster. Generally, it's right about this, but if it gets it wrong, try running analyze on the database and running the query again to see if it's you can get the if just the planner statistics were out of whack. Well, that didn't work. Try turning off sequential scan. Force it to do an index scan, and see how long it takes to use the index. Then, you often will be unpleasantly surprised that Postgres was right the first time, and it takes much longer to use the index. And then you go, wait, it didn't even use the index then. Sometimes there are indexes it can't use. For example, the query is written in such a way that the index isn't applicable. The index is invalid. That's a relatively unusual situation, but you can try dropping and recreating the index. Or it's an expression index, and Postgres isn't able to map the indexes, the expressions, to realize it's the same one. Try doing a very simple query on just that field and build the query back up from there and see how that works. And sometimes Postgres is right, but it's wrong. That sometimes the index is faster even though Postgres thinks it won't be. Often random page cost is out of whack here. If you have the original random page cost setting, that will frequently do it. Another thing that didn't make it on the slide, but effective cache size set too low can often force it to not use indexes, so make sure effective cache size is correctly. Sometimes also doesn't have enough statistics for a field. The statistics are just a per field histogram. Normally it's 100 buckets, but try cranking up to 1,000 buckets and see if that higher resolution helps. You can do that there's an alter table command to change the statistics. And sometimes just the query plan sucks. Here's an example query plan. Explain, of course, this is the output from explain, which everyone knows is extremely readable. What this is doing is it says, okay, I'm doing a scan on this index, looking for this field, PID equals that value. I'm then doing this bitmap heap scan, and then I'm rechecking it, and then a bitmap index is like, what is this? Why is it doing all this stuff? Well, what happens first is it scans the index and builds a bitmap of pages, not tuples, because there are multiple tuples on a disk page, that contain candidate results. It then scans the heap, which is what Postgres calls the actual database, that's not the index, retrieving those pages. And then it rechecks the condition against the tuples on those pages. Why is it doing that? Why is it doing that? It does that when it thinks there's a large number of tuples to be retrieved, because it avoids doing a lot of random access to the disk. By comparison, a pure index scan is going to look like this. Index condition is this, index scan, bang. 2 rows. And we have a keynote failure there. So when you see that multiple level bitmap index scan followed by a bitmap heap scan, it thinks the number of pages of tuples that's going to hand back are relatively large. If it's wrong, that may be a good time to reanalyze the database. You can create an index with either create index or create index concurrently. Just a quick note. Create index is a single scan of the table building the index. It uses maintenance workmem. That's one of the things maintenance workmem is for, to do the creation. The problem is it takes exclusive lock on the table, so nothing else can touch that table while it's going on. You can also do a create index concurrently, which does 2 passes, builds the index and validates the index. If the validation fails, which generally means you're creating a unique index and somebody blew the unique constraint while the index creation was going on, it'll be marked as invalid, and you can't use it, so just drop it and create it again. It takes a lot longer than a create index, but the good news is other people can use the table at the same time. There's also a reindex operation. Rebuilds an existing index from scratch, takes exclusive lock on the table. The only reason you generally need to do this if the index has gotten badly bloated, if you don't want the behavior of it locking the table, you can just drop the index and do a create index concurrently instead. Bloat is kind of a problem for indexes because sparse deletions within the index range can create holes in the index, much worse than in the heap. When you get the slides online, here's a query that can help you find badly bloated indexes so you can drop them and recreate them. Generally, though, don't worry about it. There are two views inside of Postgres. There's a view called pgstat user indexes, which is really handy because over time it reports the number of times the index is used. And if you see non-constraint indexes that are being used, that are not being used, drop them because they're expensive to create and maintain. So, pgstat user indexes. Okay, so occasionally things that you don't want to have happen in Postgres. How do we solve these problems? Here is the number one complaint, which sort of rolls up a lot of the previous. This query is slow. Run, explain, or explain, analyze. These prefix the query, so you say explain, select, blah, and you get output, which is somewhat cryptic. One thing I will note is we will take a look at this website, explain.pez.com, which is a way of parsing this output into something that's a little more readable. But let's look at this query, kind of your basic e-commerce query. Distinct from left outer join, blah, 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 all this stuff. And here's the output. Woo! Huh, okay, what do we do here? The important thing in reading one of these is it's a tree structure. So you read it from the, this is the root, and these are the leaves. So there's this root, which contains this, which contains these two. The way you parse this is doing an index scan on this index condition, because it's doing a join here inside this nested loop, applying this filter to the results. Postgres thinks, note that this is an explain, so it hasn't run the query. This is just what Postgres says it's going to do when you do run it. It thinks it's going to return 19 rows from this index scan. This index scan is going to walk through on subscriber ID equals this, applying this filter in addition to that. It's inside a nested loop, which is a kind of a join. The way this actually is being processed is the nested loop executes this part, and then for each result in this, executes this one. So this one says it thinks, I'm going to get back, it'll get back 16 rows. For each of those 16 rows, it'll execute this once. So, and then filling in this e-commerce order ID with the appropriate value there. It'll then pass this up to this aggregate node. The reason for that aggregate is, see this count distinct thing? That's executing the aggregate there. And the result will fly out. It says, I'm going to produce one row from the whole thing, which is what you'd expect from a statement with a count at the top. So read the execution plan from the bottom up. Look for the nodes that are processing a lot of data, especially if the data set's being reduced considerably on the way up. If you see, if the ultimate query produces 5 rows, and there's 12 million rows being processed at one point, maybe you can see a way to reduce that 12 million row operation, because that's where your problem is going to be. Remember, analyze. Planner needs statistics, create them. If the statistics are bad, the plan will be too. For example, notice this big cost thing up here. This is before I ran analyze. Then I ran analyze, and suddenly, this is before analyze. It says, well, I don't know. I have no idea what I'm doing here. I'm just going to do a sequential scan across this entire table. I don't know. I know that for sure that'll work. And I'll run a nested loop, and so for every one of these 868 rows, I'm going to do an index scan here. And I think this is going to cost that much. Then I did analyze, and suddenly the cost dropped like that because it said, oh, I get it, subscriber ID is really selective. I'm going to pick up I'm going to pick up a very small number of rows with that. Bingo, I can use the index here. So this is a great example of how just changing an analyze can get you a better query plan. There are histograms on per column basis, 100 buckets. They're not restored from backup. You have to run analyze after a backup. And when you do a major database update, they are not going to be automatically updated until AutoVacuum gets around to it, which may be a long time. Sir?
What rules of thumb do you, maybe you're about to get into this, what rules of thumb do you use to translate the cost to how long?
Allow me to answer.
As I was asking.
Perfect lead in, perfect lead in. Cost in an explain plan is measured in arbitrary units. They're shekels, they're quatlus, I don't know. They're traditionally we would call disk fetches, but what the heck does that mean? The only thing that you can do is compare them with other plans in the same database configuration. So they can be compared to two plans. If you run an explain and then run another explain, you can compare the costs reasonably to each other in that thing, but they're not milliseconds. They're not any real. You notice that there were two numbers separated by a double dot. The first number is the startup cost. It's how long it thinks it'll take to get the first tuple out of the process. And the second is how much it'll take to get all the tuples out. For some things like sorts, they're going to be identical. For things like index scans, they're going to be very different because it's very little time to get the first tuple out of the index, but it might be a long time to get all of them. If you're running same plan, other plans in the same planner configurations, then these numbers are comparable. One important note is the costs are all inclusive of subnodes. So they're summed all the way to the top. If you run explain analyze, it'll give you the actual time it took to run the query. It'll actually execute the query. Be careful if you say explain analyze delete, because it actually did it. And it gives you the actual time in wall clock milliseconds. So note that wall clock time, not query execution time. It also presents total time, and they're also inclusive of subnodes. Both of these, both actual and estimated, have rows counts. It's not the number processed, it's the number that node handed up. So for example, if there's a filter on it that took out 90% of the rows, it's the number that passed the filter, not the total number it looked at. So that's one of the first places to look for something being out of whack, especially bad planner statistics, is if it estimated that something would take a small number of rows, but it really returned a large number of rows, or vice versa. So scan the plan looking for those kinds of large mismatches. By large, I mean about a factor of 2 or more. Within a factor of 2 is acceptable for planning purposes. There's also a loops value. It's the number of times each subplan was executed by its parent. In those cases, the actual times are averages, not totals. So you have to multiply it by the number of loops to get the total time that particular node was executed. So things that are bad. Joins between two very large tables. They're it's very hard to execute those efficiently unless the number of rows that are going to come out is very small and a predicate, that is to say part of a where clause, can really reduce them. So joining two 20 million row tables is going to take a long time. Cross joins, that's a join where every row is joined with every other row in the other side. They're also called a Cartesian product, because if you join a 1,000 row table by a 1,000 row table, you get 1,000,000 rows out. It's multiplicative. I think once in my entire career I've done that on purpose, but you do it all the time by accident if you put two tables in the from clause of a query and don't put a join criterion in. By default, you're going to get a cross join. So these can be created by accident. Make sure you're not doing one of those. The other one is if you see a sequential scan on a large table. Sometimes it has to do that, but that's a very good place to look for. Maybe you can add a predicate, maybe you can add an index. Everybody complains about this. The first thing, lots of people, they load up this giant database, they log in, they do select count star from a table, and this always results in a full table scan in Postgres. And it's not very fast, so don't do that. So the reason is this number, because it's this number, because we want it to work right, this number is exactly accurate. The problem is that means we have to look at every single tuple to see if it's visible or not to the current transaction. Really common problem, offset limit. This is everyone's favorite way of implementing pagination. You know, you have a blog application, and you know you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 down on the bottom, and you click, and you're implementing this by offset limit. Offset is implemented exactly the least intelligent way you can imagine implementing it in Postgres. It runs the query and throws away that many rows. It's actually hard to come up with a better way of executing it, actually. But so the problem is, this means that if you're clicking on 536 down here and you have 10 entries per blog, it's throwing away the first 5,000 odd entries on the query. So for low offset values, this is okay, but it really comes apart fast when you have high offsets. And you think, but humans never do that. You're right, humans never do. Googlebot does. Googlebot will click through all 25,000 of those links and slow your database down. So this is a good thing. You can either pre-calculate or use other keys like date ranges or things like that for high pagination values. So be aware of that. Okay. Then someone could say, the database is slow. And you say, what do you mean the database is slow? And they said, I just told you, the database is slow. So the first thing is like, well, what's going on? Look at PG stat activity. This is a view inside of Postgres. It will be kind of uninteresting on these little toy databases, but happy to show you anyway. You say select star from PG stat activity. And it tells you all sorts of things. It tells you the OID, the object ID of the database, the name of the database. This is a lot more useful to you. The process ID in the operating system of the back end that's running this query. Don't worry about that. This is the username. This is the application name. The application is something that the application who connects to Postgres sends along. It's often empty for web applications and things like that because you have to set it manually. Client host name and client port. Since I'm connecting locally, these are uninteresting. This is the timestamp that the backend started. That is when the client connected to Postgres for the first time. This is when the current transaction started. This is when the current query within that transaction started. This is the last time there was a state change inside of that query. This is a really super important column, this Boolean. This says, is it waiting for a lock? If you see a lot of queries that are waiting for locks, that's very, very interesting. That can be, this is what state it's in. Active means it's actually running the query. You should either see, everything should be either active or idle. If you see idle in transaction, very bad. And this is the text of the current or the last query that was run. Super informative for what's going on in the database. One thing you can do is just tail F the logs. Oops. You know, see what's going on. Is it for example, if the database is non-responsive but not much activity is being logged, that is probably indicates a locking problem. If lots of activity is being logged, it's not. It may just be it may just be overloaded. One thing is do an IO stat and see if see what the utilization of the database IO volume is. If it's at 100% with a really long request queue, you're probably have saturated. You know, there's IO problems. For example, if this is happening on a periodic basis, like when the checkpoints are firing, you may need to increase the checkpoint timeout to spread the IO out over a longer period. And of course, there is database isn't responding. We're down. So first, make sure it's up. You know, can you connect with PSQL? Just last night, in fact, a client called and said, we're down. And I logged in with PSQL, everything's fine. Okay, so what would you like me to do, sir? Database is up, you know. So don't immediately, don't panic. Just, again, look at PG stat activity. If you're seeing a lot, if you're seeing a lot of things that are marked with true, the next thing to look at is PG locks. You spend a lot of time bouncing between these two. Oops. What did I just do? Stop that. So, PG locks, this is going to be super uninteresting because this is an idle. This is what kind of lock? The database, the relation, these are the object IDs, the page, tuple, virtual ID. What you end up doing is you look for the process ID that matches the process ID of all the things that are waiting. And you see what it's waiting for. Sometimes it'll be a particular relation or a page and tuple inside of a relation. You then rerun the query looking for the thing that holds that lock, which is to say you say where the relation has the same OID, but granted is true. And then so now then you can take the process ID and go back to PG stat activity and find the query that's holding that lock that everyone is waiting on. And if it sits if it's sitting there in idle in transaction, you kill it or something, which is frequently what you'll find. That's the best. That kind of bouncing back and forth between PG stat activity and PG locks is something you do all the time for diagnosing locking problems. One, two, three. Yay. Okay. So let's so that's a good that will get you started. And Python in particular. So let's talk a little bit about Python. This is going to be a little bit Django specific because that's kind of my thing. But any other questions you can ask? So if you're using Python 2, you're using PsychoPG2. It is the only interface library that makes any sense to use anymore. It's very feature rich. It's very Pythonic, in so much as the DB API is Pythonic, which is open to question. It's a Python PEP, so I guess it's Pythonic by definition. Things to note, though, about PsychoPG2. This is the most common mistake on PsychoPG2, is you write this big query, and you say execute, and Postgres says, OK, I've done it. And then you say fetch 1, and you get an out-of-memory error. You think, what? Well, that's because when you did that fetch 1, all 12 million rows were just handed back to you across the wire. This is part of the libpq, Postgres' own wire protocol. The way this is a very common problem in Django because, of course, Django, you read down the code and it's really trying to do the right thing. There are these fetch 100s and these generators and all this complicated machinery, none of which actually works. Because the first row, all the rows come back over the wire. And this is regardless of the result set size. So the first thing to do is when you do your queries, try not to write queries that return 12 million rows, because why are you doing that? But if you really want to do this, you need to use a named cursor. Not just the cursor object that PsychoPG2 gives you, but a named cursor, which you create when you do the execute statement, when you create the cursor object. That will get you a database side cursor, which is the way you really scroll through individual results. Be sure to dispose of it properly, because it's not just holding stuff in memory on your side, it's holding stuff in memory on the server side also. The Python 3 situation is not great. There's PyPostgreSQL, which is a Python 3 driver. One of the nice things about it is also runs on Python 2, on 2.7, is it's pure PostgreSQL. So if you're using one of the newer, fancier interpreters that require pure Python, it'll run, whereas PsychoPG2 won't, because PsychoPG2 has a large C component. I'm not sure what the development status of this is, but
I think there's Psycho CFFI now, isn't there?
is there? I don't do a lot of Python 3 work, to be perfectly honest, so since not a lot of call for it yet in the consulting world. And regarding Django, if you're running on 2.6 or higher, use the atomic decorator. Read about it and use that pattern. Cluster your write operations in small transactions and leave the read operations outside this decorator. And do all your writes at the very end of the view function. One of the things that can be an issue, if you're doing load balancing, which requires additional software, which we'll talk about, between a master and a secondary is there is such a thing as replication lag. You do a write to the master, it does take time for it to come down the connection and be applied. Django applications are blissfully tend to be free of this because of the way people tend to write view functions. They tend to do a bunch of reads, process stuff, and then do a write right at the end, which nicely avoids the replication lag problem. So follow that pattern. Let it work for you. One of the nice parts about Django is multi-database replication with hot standby, where the standby is available for reads. The multi-database stuff they added works very nicely with it. You can set it up so you can point your writes at the primary and all the reads from the secondary using the database router mechanism. That's really very cool. If you're on Django 1.5 or earlier, I modestly recommend that you use the exec decorator, which I wrote. It's actually the basis for Atomic. So if you're still on 1.5 or anything earlier, you can use this. The reason is Django applications are very, very susceptible to these idle and transaction things. There are clearly paths out of the code that will leave a transaction open if you're using sort of the standard 1.1 era transaction management tools in Django. And those can be a big problem on Django applications. So using Atomic on the new stuff or Exact on the old one will largely avoid these problems if you're rigorous about your transaction management. Use South. Use South, use South, use South. And of course in 1.7 it's built into the core, so there's no reason not to. South, for anyone, I'm sure everyone who does Django knows, but it's a database migration tool. One of the reasons to use it is both because it's very nice for just general stuff. Also, it provides you a nice hook for doing things like adding constraints, fancy indexes, and all this stuff that the Django ORM syntax doesn't let you specify. You can put in a South migration. Very, very handy. Okay, now let's talk about some special situations that can arise in Postgres that most databases don't run into, but they can happen. Actually, all of these happen eventually. Minor version upgrade. We just released 9.3.4, which everyone should upgrade if you're on 9.3, or if you're on anything earlier. Do these promptly. Don't wait. Often they are security holes that need to be patched, or they're lurking data corruption bugs. The nice part is that the only thing you have to do here is install new binaries. There's no special magic upgrade tool. On Debian, sudo apt-get upgrade will do all the right things for you. So it's really super easy to do. There is some downtime, but only long. You basically are bouncing the server and replacing the binaries. Major version upgrades, not so much. They do require a little more planning because you have to migrate the on-disk structure from the old version to the new version. You can do this with this tool PG Upgrade, which can do an in-place upgrade of the database. The database has to be down at the time, but it doesn't take, in the old days, you had to do a full dump restore of the database, and that could take a long time. Now PG Upgrade is reliable enough to recommend. Yes? There's, you either keep a backup or PG Upgrade by default makes a copy of the data. So that's, in effect, you're keeping the old one. Unfortunately, there's no way of going back. Once you step through the door, there's no stepping back. PG Upgrade does have an option where it will, instead of copying the data, it'll create hard links from the old data, which means you don't have to take the time to do the copy, which is if you're upgrading a 4 terabyte database is probably what you want to do. You can do essentially zero downtime upgrading using trigger-based replication by starting a replica on the new version, doing trigger-based replication to it, and then at the cutover moment, just pointing at the new database. That's a fairly fiddly operation, though. And dump and restore is always the safest, if not the most practical if you have a huge database. When you get a new major version, always read the release notes. Sometimes there are special data cleanup things you have to do from new to old. Plan for this. Versions of Postgres are EOL'd after 5 years of their first release. That seems like a long time, but it's amazing how time flies, especially when people resist upgrading because of the downtime. Always have a plan. You don't have to execute the plan immediately, but understand how you're going to move from one to another, or you will be one of these clients that's caught on 8.1 with a 4 terabyte database. Because 8.1 is too early to use PG upgrade. One of the things to note is all parts of our application set, the primary and all its secondaries, have to be upgraded at the same time for a major version. They all have to be on the same major version. You can't use streaming replication to do a version upgrade. Another special situation is when you bulk load data. You're loading, you get regular data, very large data feeds, or you're initializing a database with some huge set of data that's not another Postgres database, but random data. Always use copy, not insert. You will save endless time. CyclePG2 actually has a really super nice copy interface. Copy does full integrity checking and trigger processing, just like insert does. Be sure you do a vacuum afterwards, but it's much faster. Occasionally, databases that have really high insert rates. Where high is that's the primary, where you're starting to hit I/O capacity on the disk. One thing you can do to improve performance is actually reduce shared buffers considerably, so that checkpoints don't have as much to flush out, and really constrain checkpoint timeout down to 3 minutes. This is good to do if your I/O subsystem is getting totally swamped on a checkpoint. If increasing the checkpoint time doesn't seem to be helping you at all, try going the other way if your database is a very high insert rate. Make sure you're doing analyzes enough to keep the planner statistics, assuming you're querying this thing on a regular basis. Okay, so Amazon. Not too many people on Amazon, so we can go quickly on this. You know, generally, Amazon's like any other system. You know, it's servers. You know, you run things on them. One of the things to remember about Amazon in particular is that instances can just vanish out from under you with no notice. So what are you going to do about your data? Make sure you have a plan for that. One of the things to note is EBS can fail to reattach on boot. This can be a big problem, so make sure you understand this can happen. I'm kind of torn on provisioned I/O operations. This is a way of guaranteeing a particular level of performance out of EBS. Truth be told, I don't think they're cost effective. Heroku, on the other hand, absolutely swears that they're the best thing ever, and they know a thing or two about running Postgres on AWS. So generally, our clients do use them. Interestingly enough, when I by accident created an instance, a secondary next to a second secondary that used standard EBS, not PIOps, I couldn't see any performance difference between the two. So take that for what it's worth. If you're building out a large-scale one where you have a lot of servers, and this is going to be your data center, always script everything. Don't do this through the console. It's so easy to screw things up. You can use Salt, which Salt is currently my favorite tool by far. It's also written in Python, which is really nice. Use a VPC. It'll make your life a million times easier in provisioning things to put everything inside a VPC, and you have a much better security story. Use Amazon for what Amazon's good at, which is scaling up and down to meet load. Amazon's really expensive if all you're using it as is equipment rental service. If you're just buying a big server from them, that's a really expensive server you're buying. They are not that cheap. However, if you can scale up and down by adding secondaries, adding web servers, things like that, then you can get really cost-effective usage out of Amazon. Which brings us, of course, to RDS. Relatively recently, Postgres rolled out RDS, which is a managed database service. Rather than getting a server, what you get is a database instance, and here's your port to connect to, and there it is. RDS is an interesting product. It has, overall, I kind of like it. It's pretty neat. It has one huge benefit, which is it has automated failover. You create a secondary, and if the primary fails, you're automatically switched to the secondary, which is automatically promoted. This is frankly a pain in the neck to do on existing Postgres. You have to use pgpool, some scripting, things like that. So that's a huge plus. Big minus, you can't read from that secondary. As far as you know, it doesn't exist until RDS fails over. So, but you're paying for it. So that's your choice. It's other minuses are it's not cheap. It's their most expensive RDS product. You also hope you like the set of extensions that they give you because you can't install anymore. You don't have full super user access to it. Now, that being said, they do give you a fairly generous set of extensions. The one they don't give you is PG stat statements, which I'm really sorry they don't. However, it's not a bad place to start with Postgres. And you can always dump your data out of it and move to something else if you want. Really quick thing about sharding, just quickly. Eventually, when you need to shard, eventually you'll run out of write capacity on your master. You can't get a big enough server to handle all the data that's coming in. And then what? Right now, there's no integrated multi-master solution in the community version of Postgres, but we have some options here. There's a project called PostgreSX, which is an open source fork, easy for you to say, of Postgres. It's kind of, if you're familiar with Oracle RAC, it's kind of like that. It's intended to be its usage models for dedicated hardware in a single rack. It doesn't deal well with slow communication between the nodes or one node failing. So, and it's still experimental, but it's very interesting. Take a look at it. It is version 1.0. They're not calling it beta anymore. So in theory, it's ready for production. There's Bucardo, which has multi-master write capability. This is great if you have burst writes, and that's your problem. It's not great for sustained writes because ultimately the data has to be written somewhere anyway. You can also build your own solution, like distribute, where you shard the data across multiple databases by some application-based solution, like arbitrary, like a hash of user ID, or abstract, like region. The application is responsible for routing the data. I will defer to Instagram, who knows a thing or two about big databases. You can pull this out of the slides. That's a discussion of how they did their sharding architecture. A little bit about pooling. Opening a connection to PostgreSQL is kind of expensive, and it actually can be longer than the query time, especially for short queries. Django was particularly bad about this because until they added the connection reuse stuff, it opened a request on every single web request. So if you're going to use above 200 to 300 connections, use a pooler. The one we generally recommend is PG Bouncer. It's developed by Skype. It's really easy to install. It's very fast. It can handle thousands of connections. 10,000 inbound connections is usually no big deal. It doesn't do any kind of failover load balancing, though. It's really cheap and cheerful, so that's an issue. For that kind of stuff, we recommend you use HA proxy and a virtual IP. There's also PGPool 2. This does actual query analysis. It can route queries between a master and a secondary based on what it sees in the query to think it's a write statement or it's going to update the database or not, which is pretty sophisticated and pretty neat. It can do all sorts of stuff, load balancing, failover, and secondary promotion. It is, however, kind of high overhead, and it is very fiddly to install. And I just ran into a nasty bug on it yesterday. So it's not on my Christmas card list right now. Quickly, some tools that you'll probably want. Monitor everything. Use Ganglion or Nagios or whatever to disk space, CPU usage, memory usage, and replication lag. Bucardo.org has a plugin called Check Postgres that runs under Nagios that will monitor everything you can imagine about a Postgres database, of which you probably only want to turn on about 4 things. But it's very comprehensive. PGAdmin 2, comprehensive open source, almost, generally not too buggy client. There's Navicat, which is commercial product, which is not too bad, but that one's not Postgres specific. For log analysis, there is exactly one tool to use right now, which is called PGBadger, because it replaced PGFuine, which is also a small animal that digs around in logs, R. There is an extension in Postgres called PG stat statements, which is really handy and not used nearly enough in my opinion. It actually keeps track in the Postgres core of regularly used statements and collect statistics on them. It's an extension you have to install, but it's really useful. It maintains an internal buffer. And that's my presentation. To the minute, wow. Questions, please. Well, the thread pool is useful. That solves an application level problem, which is the application opening and closing connections regularly. PsychoPG2 can still be useful. For example, let's say you have 25 web servers, and you've configured you're running inside of Gunicorn or Uwizgy, and so you have 8 processes, each which have 4 threads. So you have multiply it out. You have thousands of possible connections coming in. It would be very handy if all of those could stay open all the time, but there's no possible way you want, the Postgres, the way to set max connections in Postgres, in my view, is you set it to the maximum number of simultaneous queries Postgres could execute at that moment, which is probably like 150 maximum. I've set it high as 10,000. It's like, you can't, you're not going to throw 10,000 queries at Postgres and it'll just fall right over. And in fact, it can be a real problem because Postgres generally does not fail like this. It goes this, and then suddenly it hits a threshold and starts thrashing because it runs out of something, runs out of CPU, runs out of memory, something like that. So what you want to do is set max connections just a little bit below that thrashing threshold, which of course is hard to do analytically, but you pick something like 200 or something. So you say 200 on the server side, and then as many as you want on the client side. If you try to run more than 200, PG Bouncer will start queuing them up, which overall from a throughput point of view is probably a better solution. So like Django now has thread pooling for its connections, and I think that's really great to use, but it doesn't replace PG Bouncer. PG Bouncer is pretty easy to configure from its docs, in my view. Maybe I'm wrong. There's not much to tune in PG Bouncer. Basically you have 2 numbers, the client pool and the server pool. The server pool I set to like 10 fewer connections than max connections, so I have some overhead in case it runs wild. And on the client side, however many you need to keep the application from being unhappy. Yeah, so that's the nice part about PG Bouncers. There's not much, you don't have to think too hard about it. PG Pool, the answer to your question is no, there is no good documentation anywhere. Yes?
This is kind of an esoteric question, and I don't really know much about the internals of Postgres, but when you talked about locking and rollbacks and that, you said that there's all these separate copies of the database. Clearly there's not a full copy of the database except you've got some memory. So under the covers, is it just pretty much those tuples that are affected?
It's essentially a copy on write mechanism. So when you update a tuple, you get a new copy of that tuple is created on disk.
So if you've got, say, 200 connections to the database, potentially you could have, 150 different copies of tuples.
Well, you don't, only if you've modified it. If all 150 go and touch, and each one touches a different tuple and updates it, then yeah, you've just added 150 tuples. The way to think about it as an update operation in Postgres is effectively a delete plus an insert. It deletes the old tuple and inserts a new one. The way it actually is implemented inside of Postgres is that each tuple is marked with which transaction IDs can see it, a range of transaction IDs that can see it. The documentation is okay on this. It's not great. There's also a presentation that Bruce Momjian gave at at a PGCon. So if you do Bruce Momjian MVCC, it's a pretty good explanation of how the MVCC architecture actually works.
Thanks a lot.
No problem. Sir. That's a really good question. And right now, there's no good architecture for that in Postgres. What you can't, there's every user, everybody who can connect to the database gets pretty much the same ability to run queries. You could give them each different pools to limit the number, like if you use a PG Bouncer or something like that. Give them different pools to limit the number of connections that could be in simultaneously. But is your goal something like a nice kind of operation that where they don't get as much resources? They can run whatever they want, but they don't get the same level of resourcing as a higher performance one. Nothing immediately pops to mind. You're not the first person to raise that issue, but that's give them a replica to run on. It sounds absurd, but that's actually a very common thing to do, is to spin off a replica whose only thing is data analysis. You know, the people who run these horrible data cube queries that grind the database to a stop, give them their own replica to run on. It's actually, and then they're not hurting the master or the secondaries whose job it is to stay really close to the primary for failover purposes. That's one option. Sir?
What does apt-get do on major upgrades?
Nothing. It won't audit you. The packages are all named by the major version, so you will never accidentally install a major version by just doing an apt-get update. Thank goodness, that would be bad. Sir.
I was going to ask a follow-up question to his question.
Mm-hmm.
Is there a good solution for doing data analysis on a follow database since you can't write to it equally?
Well, one thing that a lot of people do is that they will break the replication. They'll promote the secondary to being a master, and then they aren't getting updates, but they can do, at that point, you can do whatever you want to it, and then you just throw away and recreate it when you want a new copy. Something that is not uncommon is they'll have two, one of which is catching up, is active replica, one of which is detached and used for data, and then at midnight or something they promote one and start re-imaging the other one, and then it's fresh by the next midnight cycle. Nice part about cloud providers is you just provision new servers and throw them away when you're done. Any other questions? Sir? Yeah, start with. They will be at, thank you, thebuild.com. Give me about 24 hours. I will also, and that's my Twitter handle, I will announce it there. And that's PG Experts, my company's site.
Talking about RDS or something doing automatic failovers.
Mm-hmm.
In the real world, what did people do before? Did they actually edit it in big file when it was time to?
Well, either a human being did it, or we use pgpool or HA proxy, or CoroSync or Heartbeat, and some scripting based on that. It's a pain. Yeah, it is far and away the nicest thing about RDS is that's all just taken care of for you. It's annoying to do in the real world. Sir.
Yeah, you talked about when we were talking about the use of null. In the Django documentation, I think they recommend the use of reasonable defaults wherever possible. So I'm still wondering, like, you have a middle name. Do you typically default that to an empty string and then make it a?
Well, you can. I would default it to an empty string in that particular case. There's actually a U.S. convention which is quote NMI unquote for no middle name, no middle initial. That is actually the government standard, so you could use that. Unless somebody legally changed their name to have that as a middle initial, which is, I suppose, possible, a middle name. In things like that, I would generally use the empty string rather than null. I generally try to use null only the places I'm forced into it, like outer joins and adding fields and things like that. Sometimes, though, it's you have to, nulls happen, but don't go in and say, well, I'm going to say, right away, you assume it's going to be a flag value, a semantically interesting flag value from the start, because I think especially when you start writing outer joins, and you can't distinguish between a null the outer join has inserted because of the way outer joins work, and the flag value, you're going to start hating life. But there's another question over there, I thought. Yes, no? Anything else? Anything I missed? Okay. Thank you so much. This is the Google link for the survey, which will also be on the slides. But there was the much better tiny URL, which is
/PyCon 2014 survey, all one word.
like that. Vote early, vote often.